Now with all these basic terminologies, we'll be able to define classical definition of probability. Now in classical definition of probability, assumption is all the outcomes in sample space, they are mutually exclusive, exhaustive, and equally likely. Then probability of occurrence of event A, it is represented by PA, and it is equal to number of elements in event set upon number of elements in sample space. So basically it is number of favorable outcomes upon total number of outcomes. So in classical definition, assuming each sample point to be mutually exclusive, exhaustive, and equally likely, we can define probability of occurrence of any event A as number of outcomes favoring this event A upon total number of outcomes, which is simply number of elements in this event set upon number of elements in sample space. And we know that clearly NA is greater than or equal to 0. It is always less than or equal to NS. That means any probability, it will always lie between 0 and 1. So probability of an event will always lie between 0 and 1, including both 0 and 1. Now if probability of any event is 0, it means there is no outcome which favors that particular event. In that case, we'll say this A is an impossible event. And if probability of A is 1, that means whenever we are going to perform this random experiment, A is certain to happen. So in this case, this A, it is a sure event. So any probability, it will always lie between 0 and 1, both inclusive. And this is the classical definition of probability. Now, while solving problem, mostly we'll be using this definition of probability, but this definition, it does have certain limitations. Now, one very important limitation is we cannot use classical definition if outcomes are not equally likely. Consider this scenario. Probably you are sitting under a fan. Now there are two possible outcomes for this fan. Either it will stay hanging up on the ceiling, or this fan, it may come down crashing. Now these two outcomes, they're exhaustive, mutually exclusive, but they are not equally likely. If this fan has equal probability of staying up and falling down, probably you won't be sitting under it. So in real life, outcomes are generally not equally likely. Second limitation is outcomes may not be mutually exclusive. And third limitation is outcomes, they may not be exhaustive. Another limitation is if number of elements in sample space, it is very, very large or it is infinite, then also we cannot use this classical definition of probability, as we have seen in the case where sample space is either countably infinite or uncountably infinite. But with all its limitation, classical definition of probability is still widely used. And in our case, whenever we are dealing with permutation and combination problems, More often than not, we'll be using this classical definition, which is probability of A is number of elements in A upon number of elements in sample space. And to overcome limitations, generally, whenever there is a question, you'll find that it'll mention we have tossed a fair coin. Now, when we say a coin is fair, that means it is equally likely to get a head or a tail. Or we'll say we have rolled an unbiased die. That means it is not loaded in favor of any particular number. So there is equally likely chance of getting all the 6 numbers. In case of cards, it'll say we have a well shuffled deck of cards. So when it says well shuffled, that means the cards are not being set and any combination of cards is equally likely. So with use of such terminology, we'll be able to use classical definition of probability in most of the cases. Now, using classical definition of probability, everything you have studied in permutations and combinations can be turned into a probability problem. Say, for example, suppose problem in permutation and combination is we have 6 boys and 4 girls. From this, we have to select 3 students. Now, selecting 3 students, it is our random experiment. And total number of ways of selecting 3 students from 10 students, it is 10C3. Now, suppose we have to find the probability that all 3 students are boys. So this is this event A. Then number of elements in this set A is, from these 6 boys, we have to select 3 boys, and it can be done in 6C 3 ways. So this probability of getting all 3 boys, it will be number of favorable outcomes, which is total number of ways of getting 3 boys, which is 6C3 upon total number of outcomes, which is 10C3. Now suppose we have the second question, which is an event B such that it has 2 boys and 1 girl. Now probability of B is, now total number of ways of getting 2 boys and 1 girl. Now 2 boys out of 6, it can be done in 6C2 ways, and 1 girl, it is 4C1 out of total number of ways 10C3. Suppose we have this third event C, which is getting at least 2 girls. So at least 2 girls is 2 cases, either 2 girls, 1 boy, or all 3 girls. So now this probability will be, now 2 girls is 4C2 into 6C1 plus 4C3 into 6C0 whole divided by 10C3. So all the combination problems, they can be turned into probability problems. The same can be done with permutation problems. Suppose we have a word which is A, R, R, A, N, G. Now total number of words that can be formed is, suppose our sample space. Now total number of words that can be formed with all the letters of this word arranged, it is factorial 7 divided by factorial 2, factorial 2. Suppose we have to find the probability that words start with A and ends with R. Now in this case, suppose this is this event A. Now A is fixed and R is fixed. We have to arrange these 5 letters. Now it can be done in factorial 5 ways. So that's our favorable case. So this probability, it will be factorial 5 upon total number of ways, which is factorial 7, factorial 2, factorial 2. Or it could be this event B such that both A's are together. So in this, we'll use string method. So we'll take A and A together, and then we'll have RR NGE. So this probability will be, now total number of ways of arranging them. Now it is 6 objects, factorial 6 divided by 2 R's, factorial 2, and total number of cases, factorial 7, factorial 2, factorial 2. And this third one is, suppose 2 A's are not together. Now if these 2 A's, they are not together, we can use gap method. So we'll arrange all the remaining RR, NGE, and it can be done in factorial 5 divided by factorial 2 ways. And then we have 1, 2, 3, 4, 5, 6 gaps. And in these 6 gaps, we have to arrange these 2 A's, and it can be done in 6C2 ways. Divided by total number of ways, which is factorial 7, factorial 2, factorial 2. And that's your probability of this event, say event C. So whatever we have studied in permutation combinations, function related questions, grid problems, set problems, derangement, everything can be turned into a simple probability problem. So if you understand permutations and combinations well, then classical definition of probability is a piece of cake for you. Now, using this classical definition, we can also define probability of a complement. Now we know that NA plus NA naught, it is equal to NS. Now we divide everything with NS, we can write NA upon NS plus NA naught upon NS, it is equal to 1. Now this is probability of A and this is probability of A naught. So basically, if A and A naught are complementary events, then probability of A plus probability of A dash, it is equal to 1. So if we know probability of an event, we can find probability of its complement by simply subtracting it from 1, or vice versa. Now there are 2 more terms that we must know, and the first one is odds in favor. It is given that probability of odds in favor of any event is some value. Now when we say odds in favor, we simply mean that it is ratio of probability of A upon probability of A naught. And if we say odds against, then basically we are talking about PA naught upon PA. So from probability of A, we can find odds in favor and odds against. And if we are given odds in favor or odd against, we can define probability of A and probability of A complement. Say for example, suppose it says for an event A, odds in favor is 3 by 2. Now we have to find probability of A. Now we'll use componendo dividendo. We can write probability of A upon probability of A plus probability of A complement. It is equal to 3 upon 3 plus 2. Now probability of A plus probability of A naught, it is 1. So from here we can say this probability of A is 3 by 5. And the same way, suppose we are given PA naught upon PA, and it is 2 by 7. Now again we can use component dividendo. We can write PA plus PA naught upon PA. It is equal to 7 plus 2 upon 7. So in this case, probability of A is 7 by 9. And once we have probability of A, we can find probability of its complement by simply subtracting it from 1. So for this first case, it is 2 by 5. And for this case, it is 1 minus 7 by 9, and it will be 2 by 9. So we'll be using this term odds in favor and odds against in certain cases. Now there are 2 more definitions of probability, and the first one is statistical definition of probability. Now in statistical definition of probability, suppose a random experiment is conducted n times, and in those n times, this event A, it has occurred m times, then this ratio m by n, it is called as relative frequency of A. So we'll define something called as relative frequency of A. So relative frequency of this event A, it will be m by n, and probability of this event A, it will be this limit n tends to infinite m by n. That is, when n is sufficiently very large, then this relative frequency, it is equal to probability of this event A. And second definition is axiomatic approach to probability. Now in axiomatic approach, what we'll assume is, we'll assume that let S be a finite sample space and we'll define this probability as a real valued function from power set of S to R. So this P is called a probability function if it satisfies three conditions. First condition is probability of any event A or any subset, it will be greater than or equal to 0 for all subsets of S. Second condition is probability of finite sample space is 1 and probability of phi is 0. And third condition is probability of A union B equals probability of A plus probability of B if A intersection B is phi. So in this case, this image of set A in this function P, it is denoted by this PA, which is probability of event A. So in this axiomatic approach, we are taking this probability as actually some function which is defined on power set of S to real number R, satisfying these three conditions. Now the question is, a set A has 22 elements and a subset P of A is selected at random. After replacing the elements, again a subset Q of A is selected. The probability that P and Q have exactly 5 elements in common is. Now here we know that number of elements in P intersection Q, it is 5. So first we have to choose which are the 5 elements which are common to both P and Q. So from these 22, we have to select any 5. So it will be 22C5. Now we are left with remaining 17 elements. And for each of these remaining 17 elements, we have 3 choices. Either each element may go to P or Q or neither P nor Q. So there will be this 3 to the power 17. Now for total number of cases, we have 22 elements and for each element we have 4 choices. Either it'll go in P alone or in Q alone or in both P and Q or in neither P nor Q. So there'll be simply 4, 4, 4, 22 times. So this value will be 22C5, 3 to the power 17 upon 4 to the power 22. Now 22C5 is same as 22C17 and that's your option C. Now the question is, there are 17 railway stations on a railway track between A and B. The train stops at 4 intermediate stations at random. Find the probability that at least 2 of these 4 stations are consecutive. So what we'll do is, we'll do it with the exclusion. So we'll find this probability 1 minus and then no 2 stations are, probability that no 2 stations are consecutive. Now this probability will be 1 minus. Now total number of ways of choosing 4 stations, there will be 17C4. Now we have to find number of non-consecutive selection in a row. Now we have already studied that in one of the previous videos, how to find number of non-consecutive selections in a row or along a circle. Now if we have n arranged objects in a row and out of which we have to select k non-consecutive objects, it is given by n minus k plus 1 ck. So it will be this 17 minus 4 plus 1 C4. So this probability will be
1 minus 14C4 upon 17C4. Now this is 1 minus 14, 13, 12 and 11. And this is 17, 16, 15 and 14. Now 14 will cancel. Now this is 3 and 4 and this is 5. So this value is 1 minus 143 upon 340, which is 197 upon 340.
Now here the question is, a determinant is chosen at random from a set of all determinants of order 2 with elements 0 or 1. Find the probability that determinant chosen is negative. Now, in 2 cross 2 determinant, we have 4 positions, and for each position we have 2 choices. So there will be 2 to the power 4, that is 16 determinants possible altogether. Now, when we have all 4 zeros, so that's just one case, and in this case, determinant of this matrix will be 0. Now we have the second case when one of them is 1 and 3 of them 0, and this one, it can occur in any of these 4 positions. So we have 4 cases here. So if this was one case and these are 4 cases. Now here also determinant of A, it is 0. Now we have this third case when we have 2 ones and 2 zeros. Now if we arrange them together in one row or one column, we have 4 cases, and in these 4 cases determinant of A will be 0, and then there will be these 2 cases when we have 1 0 0 1 and 0 1 1 0 where the determinant is non-zero. Now in this case determinant is 1, and in this case determinant is minus 1. We have 1 4 4 and these 2 cases. So altogether now we have 10 11 cases. Now fourth case is when 3 of them they are 1s and 1 of them it is 0. So here we have 4 cases. Now in this, if 0 occurs along principal diagonal, then the determinant it will be minus 1. So for the 2 cases, determinant is minus 1, and if 0 lie along this other diagonal 1 1 0 1, then determinant of A will be 1. So out of these 4 we have 2 choices here. So 2 here and 1 here. And then finally we have this final case when all the 4 they are 1s. In that case also determinant of A is 0. So this probability that determinant of A is less than 0 will be given by 3 by 16. And if the question is determinant of A greater than 0, so for greater than 0 we have this 1 case and 2 case here. So it will be this 3 by 16. And if we are supposed to find determinant of A equals to 0, then we have 9 and 1 10. So there will be 10 by 16. Now here the question is 10 boys and 2 girls are divided into 3 groups of 4 each. Now the probability that the girls will be in different groups is. Now what we'll do is, first we'll find total number of ways to distribute them. Now total number of ways in which we can distribute them in 3 groups of 4 will be factorial 12 divided by factorial 4 3 times and then factorial 3. Now we need to find this favorable case when the girls are in different groups. So what we'll do is we'll actually take up these 10 boys and we'll distribute them in a group of 4 3 3, and it can be done in factorial 10, factorial 4, factorial 3 square into factorial 2, and now we can distribute 2 girls in these 2 groups in factorial 2 ways. So now these 2 girls they'll be in separate group. So this required probability will be this factorial 10 divided by factorial 4 factorial 3 square upon factorial 12 factorial 4 cube and factorial 3. Now this is factorial 10 factorial 4 factorial 3 factorial 3, and here it is factorial 12, and this is factorial 4 factorial 4 factorial 4, and this is factorial 3. Now factorial 4 will cancel, factorial 3 will cancel. Now this is 3 into factorial 4, we'll have 4 here, and this is factorial 10, it will be this 12 into 11, and factorial 4 is 4 into 3 into 2. Now here 12 will cancel. So this probability will be simply 8 by 11, and that's your option 4. Now we need to find the probability that birthdays of 6 different persons will fall in exactly 2 calendar months. Now total number of ways, for each person we have 12 choices. So it could be any one of the 12 months. So there will be 12 into 12 into 12, 6 times. So 12 to the power 6. Now the probability that birthday of 6 different persons will fall in exactly 2 calendar months. So which 2? It can be selected in 12C 2 ways. Now for each person we have 2 choices. So it will be 2 into 2 into 2, 6 times, and then minus 2 cases when we have all the 6 in any one month. So there will be 2 to the power 6 minus 2. So answer to this question is 12C2 2 to the power 6 minus 2 upon 12 to the power 6, and that's your option 3. Now here the question is, using the vertices of a polygon having 8 sides, a triangle is constructed at random. The probability that triangle so formed is such that no side of polygon is the side of triangle is. Now we need to find this probability. Now first, from these 8 points, number of triangles that can be formed is 8C3. Now what we'll do is, from the total, which is 8C3, we'll subtract all those triangles in which they have a side common with that of polygon. Now we have 2 cases. Case 1, when 2 sides are common. So if 2 sides are common, we have to select 3 consecutive vertices, and 3 consecutive vertices from the n cyclic vertices can be selected in simply n ways. So it can be done in only 8 ways. Now minus, and then in this case, when exactly one of the side is common. Now we can select any one side in 8C1 ways. Now we cannot select these 2. So that means from the remaining 4, we have to select any one, and that can be done in 4C1 ways. Now 8C3 is 8, 7, 6, and this is 3 into 2. So it will be this 56 minus 8 minus 32 upon 56, and which is 16 by 56. And this is 2 by 7. So this probability is 2 by 7, and that's your option 3. We can also solve this question using non-constitutive selection on a circle, for which I have already given a formula in one of the videos. You can refer to that video of non-constitutive selections. Now the question is, 5-digit numbers are formed in all possible ways using the digits 0, 1, 2, 3, 5, 6 without repetition. If one such number is selected at random, find the probability that it is divisible by 5. Now first we'll find how many 5-digit numbers altogether can be formed from these digits. Now for the first place, now it is a 5-digit number. For this first place, we have 5 choices. Now for the next one again, we have 5 choices. So it will be 5 into 5, and then 4 into 2 into 1. So it will be 120 into 5, and there will be 600 numbers. So altogether we have 600 numbers which can be formed from these digits. Now in the first case, it says find the probability that number is divisible by 3. Now it will be divisible by 3 if sum of the digits is divisible by 3. Now if we look at sum of all the digits, so it is 1 plus 2 plus 3 plus 5 plus 6, there will be 12, 12 plus 5,
17. Now L be a multiple of 3. If we discard this 2, then we are left with 0 plus 1 plus 3 plus 5 plus 6, or if we discard this 5, then we have 0 plus 1 plus 2 plus 3 plus 6, and there is no other possibility. Now here, total number of 5 to 8 numbers that can be formed is factorial 5 minus all those numbers that start with 0. So it will be factorial 5 minus factorial 4, and here too will be factorial 5 minus factorial 4. So this required probability is 2 times factorial 5 minus factorial 4 divided by 600. Now factorial 5 is 120. 120 minus 24, it is 96. So it will be 2 into 96 upon 600, which is 8 by 25, and that's your option B. Now the second one is find the probability that it is divisible by 6. So for this, now we know that number is divisible by 3 if it is formed with either 0, 1, 3, 5 or 6, or with 0, 1, 2, 3 or 6. Now from these digits we have to form an even number. Now we have this first case when the number ends with 0. If the number ends with 0, then the number of such numbers is factorial 4, and if the number ends with 6, then it will be factorial 4 minus factorial 3. Now factorial 4 is 24 and factorial 3 is 6, so there will be simply 18. So it will be 24 in this case and 18 in this case. Now here too, if the last one is 0, then we have factorial 4, which is 24, and if the last one is either 2 or 6, then it will be this 18. So this probability will be this 24 plus 18 and then 24 plus 18 into 2 divided by 600. So it will be 102 divided by 600, which is simply 17 by 100, and that's your option C. And finally, it is the probability that it is divisible by 5 but not divisible by 4. So for this third one, it should be divisible by 5. So we have two cases. Case 1, if the last digit is 5, if the last digit is 5, then we have to fill remaining 4 digits with 0, 1, 2, 3 and 6. Now for this first place, we have 4 choices. For the next one, again we have 4 and then 3 and then 2. So there will be 96. And then we'll have the numbers which will have 0. But then it should not be divisible by 4. So we can have 10. We cannot have 20. We can have 30. We can have 50. And we cannot have 60. Now, if it is 10 here, now we are left with 4 numbers, 2, 3, 5 and 6. So for this first one, we have 4 choices. Next one, we have 3 and then 2. So there will be 24 and it will be 24 for all the 3 cases. So this required probability will be 96 plus 3 into 24 upon 600, which is 168 upon 600, and we can simplify it to 7 by 25, and that's your option A. Now the next one is 5 ordinary dice are rolled at random and sum of the numbers on them is 16. If K is the probability that number shown on each is any one from 2, 3, 4 or 5, then 49K is. Now this is a conditional probability question. We have to find the probability that number shown is any one from 2, 3, 4 or 5 when we are given that the sum of numbers on it is 16. Now what we'll do is first we'll find the total number of ways in which we can get sum of numbers on 5 ordinary dice as 16. Now we have to use
binomial, so we need to find coefficient of x to the power 16 in this binomial expansion of x plus x square plus x to the power 6 to the power 5. Now we can take x to the power 5 common, so it will be x to the power 11 in 1 plus x up to x to the power 5 to the power 5, or coefficient of x to the power 11 in 1 minus x to the power 6 to the power 5 into 1 minus x to the power minus 5. Or we can write this as coefficient of x to the power 11 in 1 minus 5 x to the power 6 into 1 minus x to the power minus 5. Now for this, what we need is, we need 1 into coefficient of x to the power 11 in 1 minus x to the power minus 5, and then minus 5 into coefficient of x to the power 5 in 1 minus x to the power minus 5. Now this is 11 plus 5 minus 1, C11, and then minus 5 into 5 plus 5 minus 1, C5. So it will be 15C4 minus 5 into 9C4, and which is 1365 minus 5 into 9C4, which is 126. So this value will be 735. So there are 735 ways in which the sum of numbers on 5 dice will be 16. That's a number of elements in case sum is 16. Now our favorable event is when we get 16 from these 4 numbers. So that means now we have to find coefficient of x to the power 16 in, now we are given numbers 2, 3, 4 or 5. So it will be this x square plus x cube plus x4 plus x to the power 5 and this to the power 5. Now here we'll take x to the power 10 common. So we need coefficient of x to the power 6 in 1 plus x square plus x cube to the power 5, or we can write this as coefficient of x to the power 6 in 1 minus x to the power 4 to the power 5 into 1 minus x to the power minus 5. That is coefficient of x to the power 6 in 1 minus 5x to the power 4 and then 1 minus x to the power minus 5. Now here we can write coefficient of x to the power 6 in 1 minus x to the power minus 5 and then minus 5 into coefficient of x square in 1 minus x to the power minus 5. Now this is 6 plus 5 minus 1 C6 and then minus 5 into 2 plus 5 minus 1 C2. Now this is 10C6, which is 10C4 and then minus 5 and here it is 6C2. Now 10C4 is 210 minus 5 and 6C2 is 15. So this value will be 210 minus 75, which is 135. So that's your favorable cases. Now we can work out this probability. So this probability will now be 135 upon 735, which is 9 by 49. And the question, it says this probability is k and we have to find the value of 49k. So if we look at this 49k, the value of 49k is simply 9. So answer to this question is simply 9. Now here the question is 6 letters are written by a person to his 6 friends. The address of each friend is written on 6 envelopes. Letters are put in the addressed envelopes at random. Then find the probability that no letter goes into correct envelope. Now this is nothing but this is D6, that is D arrangement of 6.
Now this is factorial 6. 1 minus 1 upon factorial 1 plus 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4 minus 1 upon factorial 5 plus 1 upon factorial 6. Now it'll cancel. Now factorial 6 is 720. Now 720 divided by 2, 360. 360 divided by 3, 120. 120 divided by 4, 30. 30 divided by 5, 6. And this is plus 1. So this value is 391 minus 126, and which is 265. So this required probability is 265, and total number of ways of distributing these 6 letters in 6 envelopes, it is factorial 6, which is 720. So it will be this 265 upon 720. Now this is 53, and here it is 144, and that's your option B. Now the next one is the probability that exactly 2 letters go into correct envelopes. Now which 2? So from these 6, we have to select these 2. So it will be 6C2 into derangement of 4 letters. D4 divided by total, which is factorial 6. Now 6C2 is 15 and D4 is factorial 4, 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4. Now this is 24 by 2, 12. 12 divided by 3, 4, and plus 1. So this is 9. So it will be 15 into 9 divided by 6, 5, 4, 3, and 2. Now this is 15. Now this is 3. And this is 2. So this value will be simply 3 by 16. And that's your option A. Now the next one is the probability that at least 2 letters go into wrong envelopes. Now for this third one, at least 2. This probability will be 1 minus either probability that no letter is in wrong one, or exactly 1 letter is in the wrong envelope. Now this is a 1 minus. Now if all the letters are in correct envelope, then this probability is 1 by factorial 6, which is 720. Now if you look at this probability that exactly one of them is in wrong envelope. Now once we have 1, 2, 3, 4, 5, 6, and here it is 1, 2, 3, 4, 5, 6. Now it means that exactly one is in wrong, then other 5, they have to be in the same correct position. Now if 5 of them are in correct position, then the 6th one, it cannot be in the wrong position. So this probability is actually 0. So the required probability is 719 upon 720, and that's your option D. Now the question is 16 players S1, S2 up to S16 play in a tournament. They're divided into 8 pairs at random. From each pair, a winner is decided on the basis of game played between 2 players of the pair. Assume that all players are of equal strength. Find the probability that exactly one of the 2 players S1 and S2 is among the 8 winners is. Now first we'll find total number of possible combinations. So total number of possible combinations is given by total number of pairs that can be made from these 16 pairs. So we have 16 pairs and we have to make pairs of 2, 2 and 2 8 times. So that will be factorial 16 upon factorial 2 to the power 8 into factorial 8. So that is our total number of cases. Now for the favorable case, when exactly one of the 2 players is among the 8 winners, we have to consider 2 possibilities. First possibility is when S1 is paired against S2. Now if S1 and S2 they are paired against each other, then exactly one of them will be a winner. That means we have to distribute remaining 14 players in the pairs of 2 and 2. So there will be factorial 14 upon factorial 2 to the power 7 and factorial 7. And the second case, when S1 and S2 they are not paired against each other. And such pairs will be this total possibilities, which is 16 to the power 8 factorial 8 minus factorial 14 to the power 7 factorial 7. Now we have two pairs, suppose S1 and Si and then S2 and Sk. Now we need to find the probability that exactly one of them wins. Now probability of S1 winning, it is 1 by 2, and probability of S2 losing is 1 by 2. So we have two cases, either S1 is going to win and S2 is going to lose, or S2 is going to win and S1 is going to lose. So this is the variable number of case in this second case. Now we'll calculate this required probability. Now this required probability will be this variable cases factorial 14 2 to the power 7 factorial 7 upon factorial 16 2 to the power 8 factorial 8 plus factorial 16 2 to the power 8 factorial 8 minus factorial 14 2 to the power 7 factorial 7 upon factorial 16 2 to the power 8 factorial 8 into 1 by 2. Now first we'll calculate this probability. Now this is factorial 14 2 to the power 7 factorial 7, and this is factorial 16 2 to the power 8 and factorial 8. Now this is 2, this is 8, and here will be this 16 into 15. Now this is 1 by 15. So this probability is simply 1 by 15. So we can write this as 1 by 15. Now this is 1 minus 1 by 15 into 1 by 2. So this is 1 by 15 and this is 7 by 15. So the required probability is simply 8 by 15, and that's your option C. Now it says 6 faces of a die are marked with numbers 1, minus 1, 0, minus 2, plus 2 and 3, and the die is thrown thrice. The probability that sum of the numbers thrown is 6 is. Now we have thrown this die thrice and we have to find the combination such that sum of numbers is 6. So we'll get 6 when we have 3, 3 and 0. We can also get 6 when we have 2, 2 and 2, or it could be 3, 2 and 1, and there is no other combination possible. Now for this first one, it should be 3, 3 and 0, and this 0, it can occur at any one place, so it will be this 3C1. Now probability of choosing 3 will be 1 by 6, and then again it will be this 1 by 6, and probability of choosing 0 will be this 1 by 6. Now here it will be all 2's, which is 1 by 6 into 1 by 6 into 1 by 6, and here it will be this 3 to 1, and which is possible in factorial 3 ways, and again it will be this 1 by 6 into 1 by 6 into 1 by 6. So this required probability will be 3 plus 1 4, 4 plus factorial 3 10, 10 by 2 1 6, and that's your option 3. Now here the question is the probability that in a group of n people, at least 2 of them will have the same date of birth of a non-leap year, assuming a year to have 135 days. So this required probability we have to find out using its complement. So what we'll do is we'll find 1 minus and the probability that none of them they have the same date of birth. Now for these n people each, we have 365 possibilities. So total number of possible combinations will be 365 to the power n. Now for each of these n people, we must select n possible dates, and it can be done in 365 p n ways. So this required probability is 1 minus 365 p n upon 365 to the power n, and that's your option 1. Now here the question is, consider the experiment of distribution of balls among urns. Suppose we are given m urns numbered from 1 to m, among which we are to distribute n balls which is less than m. Let PA denote the probability that each of the urns numbered 1 to n will contain exactly one ball. Then answer the following. If the balls are different and any number of balls can go into any number of urns, then PA is equal to what? Now PA is when the urn from 1 to n will contain exactly one ball. Now first we'll find total number of possible cases. Now for each ball we have m choices. It can go to any of these m urns. Now for the first ball we have m choice. For the second ball also we have m choice. So for all the n balls we have m choices each. So total number of possible combinations will be simply m to the power n. Now for this event A to occur, n balls must go into n urns. So basically it is a bijection between the two sets. So these n balls can be distributed in n urns in factorial n ways, and the required probability is factorial n upon m to the power n, and that's your option B. Now the second one is, if the balls are identical and any number of balls can go to any urn, then this PA is equal to what? Now first we have to distribute these n balls in m distinct urns. Now this is x1 plus x2 plus xm, and it must be equal to n, where x1 is number of balls in first urn, x2 is number of balls in second urn, and xm is number of balls in nth urn, and it should be n. And we have to find number of non-negative integral solutions of this equation. And we know that number of non-negative integral solution is given by m plus n minus 1 c m minus 1. So total number of cases will be m plus n minus 1 c m minus 1. Now the favorable case is PA when each of the urn numbered from 1 to n gets one ball each. Now since all the balls are identical, there is only one way in which we can distribute one ball each to first n urns. So this required probability will be 1 upon m plus n minus 1 cm minus 1, and that's your option B. Now it says, if the balls are identical but at most one ball can be put in any box, then PA is equal to what? Now if only one ball can be put into one box, then total number of ways of distributing these balls will be, now from these m urns we have to choose any n urns, which can be done in MC n ways. And once we have chosen n urns, then these balls, they can be distributed in only one way because the balls are identical. Now again PA, n balls are put into first n urns, so it will be simply 1. So this required probability will be 1 upon MCN, and that's your option D. Now here the question is, a set A contains 10 elements. A subset E of A is selected at random, and after noting all the elements, they are replaced. Again, a subset F of A is selected at random. Now, first one is, find the probability that E and F have no common elements. Now, first is total number of ways of selecting these two subsets E and F. Now, for each element, we have 4 choices. Either it will belong to E only, or it will belong to F, or it will belong to E intersection F, or it doesn't lie in E and it doesn't lie in F. So total number of ways of choosing these two subsets E and F, it is given by 4 to the power 10. Now when E and F have no common elements, then for each element we now have only 3 choices. So there will be simply 3 to the power 10. So this required probability is 3 to the power 10 upon 4 to the power 10, and that's your option D. Now the next one is probability that E and F have equal number of elements. Now suppose they have, now for this again, total number of choices, it will be 4 to the power 10. Now they have equal number of elements. The first possibility is both of them, they are null set. So in that case we have to choose 10C0 and 10C0. So it will be this 10C0 square. Now one element in E and one in F. Now one in E is 10C1 and one in F is also 10C1. So it will be this 10C1 square, and it'll continue and it'll go all the way up to 10C10 whole square. Now we know that NC0 square plus NC1 square up to NCN square, it is given by 2NCN. So it will be this 20C10 upon 4 to the power 10 And that's your option A. Now the third one is probability that E and F have exactly 3 elements in common. Now which 3? We have to select these 3 elements. So it will be this 10C3. Now for the remaining 7 elements, we have 3 choices, either E or F or neither E nor F. So there will be 3 to the power 7 whole divided by 4 to the power 10. Now 10C3 is 10, 9, 8 into 3 to the power 7. And this is 3, 2 and 4 to the power 10. Now this is 3. This is 4. Now we'll take it here and we'll divide 4. So it will be this 4 to the power 9. So we can write this as 10 into 3 to the power 8 upon 4 to the power 9. And that's your option B. Now the question is, there are 2 red, 2 blue, 2 white and a certain number greater than 0 of green socks in a drawer. If 2 socks are taken at random from the drawer without replacement, the probability that they are of the same color is 1 by 5, then number of green socks are. Now suppose number of green socks is n. Total number of socks we have is 2 plus 2 plus 2, 6, 6 plus n is n plus 6, and from n plus 6, we have to select any 2. Now favorable cases, when both of them they are the same color, so it could be either 2 red, so it will be this 2C2, or 2 blue, or 2 white, or 2 green, and this probability is 1 by 5. Now this is 3 plus n minus 1 by 2, and here it is n plus 6 into n plus 5 divided by 2, and this is 1 by 5. Now this is 6 and 5 into 6 is 30 plus 5 n square minus 5n, and it will be equal to n square plus 11n plus 30. Now 30 will cancel. We can write this as 4n square minus 16n equals 0. So value of n here is simply 4. And that is the answer to this question. And the third question is, 2 different numbers are taken from the set 0, 1, 2, 3 up to 10. The probability that their sum and positive difference are both multiple of 4 is x by 55. Now 2 different numbers, it can be taken in 11C2 ways, which is 55. Now we have to find 2 different numbers such that their sum and their difference, it is both multiple of 4. Now sum and difference, they are both multiple of 4 if both of them they are either even or both of them they are either odd. Now one of the possibilities 04, 08, and then we'll have 26 and 210. Then we have 48 and 610 is 4, but 5 plus 1 is not a multiple of 4. Now 7 plus 1 is a multiple of 4, but 7 minus 1 is not a multiple of 4. And the same way 9 minus 1 is 9 plus 1 is not. And if we look at 7 and 3, sum is not multiple of 4. 9 minus 3 is not a multiple of 4. 5 and 9, sum is not a multiple of 4. So we do not have any option for odd numbers. So this required probability is this 6 upon n, which is 6 by 55. So here the value of x is simply 6. Here the question is, 12 identical coins are distributed among 3 children at random. The probability of distributing so that each child gets at least 2 coins is k by 13. Then find the value of k. Now first we'll find total number of ways of distributing 12 identical coins in 3 children. Now suppose the first child gets x1, second gets x2, and third child he gets x3. So total we have 12 coins, and each of xi should be greater than or equal to 0. We have to find number of non-negative integral solutions. So total number of cases will be n plus r minus 1 c r minus 1, and that will be 14C2 and 14C2 is 7 into 13. Now we need to find favorable number of case. Now we have this favorable number of case when each child gets at least 2 coins. Now if each child gets at least 2 coins, what we'll do is we'll replace this xi with xi dash and we'll write xi dash as xi plus 2. So here xi dash will be greater than or equal to 0. Now we replace each of them, it will be this x1 dash plus x2 dash plus x3 dash and that will be equal to 6. Now we need to find number of non-negative integral solutions. So total number of favorable cases will be 6 plus 3 minus 1 C, 3 minus 1 and that will be 8C2 and 8C2 is 4 into 7. Now we need to find this required probability. So this required probability is favorable case which is 4 by 7 upon 7 by 13. So it will be this 7 by 13. So this 7 will cancel. So this probability is 4 by 13 and it is given in the form k by 13. So clearly value of k is 4 in this case.
Now here the question is, let S be the sample space of random experiment of throwing simultaneously 2 unbiased dice with 6 faces numbered from 1 to 6. Let EK be the set AB such that A into B is K for K greater than 1. And if PK is probability of EK where K is greater than or equal to 1, then the correct among the following is. Now if we look at this P1 and P1 is basically this probability of E1 and E1 is when product of both the numbers is 1. So this is only one case and that is 1, 1. So this probability is simply 1 by 36. Now if we look at P30, P30 is probability that this product is 30. We get this product as 30 if it is either 5, 6 or 6, 5 and there is no other possibility. So here it will be 2 by 36. Now P4 is this product is 4. Now choices we have here is 1, 4, 2, 2 and 4, 1 and this is 3 by 36 and then we have P6 which is probability that this product is 6. Now it will be this 1, 6, 6, 1, 2, 3 and 3, 2. So it will be this 4 by 36. So clearly P1 is less than P30 is less than P4 is less than P6 and that's your option 1. 3 A's, 3 B's and 3 C's are placed randomly in a 3 cross 3 matrix. So if we have a 3 cross 3 matrix, then we have 9 positions and in these 9 positions we have to arrange 3 A's, 3 B's and 3 C's. Now total number of ways of doing it will be factorial 9 divided by factorial 3 and factorial 3. Now it says find the probability that no row or column contain 2 identical letters. Now there will be no row or column containing 2 identical letters if it is of the form ABC, BCA and CAB. Now we can arrange these 3 rows in factorial 3 different ways. So there will be 6 ways in which we get different matrices. We can also arrange them along the columns. So again it will be this factorial 3 that is 6. So favorable number of cases where no row or column will contain 2 identical letters is 12. So this required probability will be 12 upon factorial 9, factorial 3, factorial 3, factorial 3. Now this is 9, 8, 7, 6, 5, 4, 3, 2. Now this 6 will cancel. 36 will also cancel. Now this is 6, 2 and 4. So this probability will be 1 by 140. Now it is of the form P by Q. So the value of P plus Q is 141 and that's your option C.
Now here the question is, a set contains 3n members. Let P and be the probability that S is partitioned into 3 disjoint subsets with n members in each subset such that the 3 largest members of S are in different subsets. Then we need to find this limit n tends to infinite Pn. Now first we'll find total number of ways of distributing these 3n members in 3 subsets. Now it can be done in factorial 3n divided by factorial n, factorial n, factorial n 3 times. And since we are partitioning it, these 3 subsets, they are identical. So that is a total number of ways of partitioning this set. Now for favorable cases, we have 3 largest members of S. Now suppose there are L1, L2 and L3. Now we are left with 3n minus 3 members which are to be distributed in n minus 1, n minus 1 and n minus 1 ways. Now it can be done in 3n minus 3 factorial upon n minus 1 whole cube divided by factorial 3. Now in this case, since we have 3 different people, so we can arrange these 3 groups in factorial 3 ways. So this, for this favorable, this factorial 3 will cancel. So this required probability Pn will be factorial 3n minus 3 upon n minus 1 factorial cube divided by factorial 3n factorial n cube into factorial 3. Now it will be this 6n cube and here will be this 3n minus 1 and 3n minus 2. Now this 3n will cancel, so we get 2n square. Now we take this limit n tends to infinite. Here coefficient of n square is 2 and the denominator coefficient of n square is 9. So answer to this limit is 2 by 9 and that's your option D. Now here the question is, Mr. A randomly picks 3 distinct numbers from the set 1, 2, 3, 4 up to 9 and arranges them in descending order to form a 3-digit number, and Mr. B randomly picks 3 distinct numbers from the set 1, 2, 3, 4, 5, 6, 7, 8 and also arranges them in descending order to form a 3-digit number. Now the first question is, find the probability that Mr. A's 3-digit number is always greater than Mr. B's 3-digit number. Now this first case, this number has to be always greater. Now difference between this set and this set is, this set has 9. So if 9 is chosen by Mr. A in one of the 3 numbers, then in that case, number formed by Mr. A will always be greater than number formed by Mr. B. Now in how many ways 9 can be selected? So we need 3 numbers, out of which 1 is already selected. So from the remaining 8, we have to select any 2, divide by 9C3. Now this is 8, 7, 2 and this is 9, 8, 7 and this is 3 into 2. Now 8, 7 will cancel, 2 will cancel. So this probability is 1 by 3. So there is this 1/3 probability that Mr. A's 3-digit number is always greater than Mr. B's 3-digit number. Now the second question is the probability that A and B has the same 3-digit number. Now for the second part, they'll have same 3-digit number if Mr. A picks 3 numbers from 1 to 8 and Mr. B also picks number from 1 to 8. Now for this, A must not pick 9. The probability that A is going to pick 9 is 1 by 3. Then the probability that A will not pick 9 will be 2 by 3. Now we have 8 numbers available to both, and from these 8 we have to select any 3. It can be done in 8C3 ways. Now Mr. B, it must choose the same number, so it will be simply 3C3 divided by 8C3 and 8C3. I'll cancel. Now this is 2 by 3 and this is 1 and 8C3 is 56
28, 84. So this probability is 1 by 84. Another way of doing it can be, for Mr. A, he must choose any one out of 8. So it will be this 8C3 divided by 9C3, and B must choose any one. So it will be 1 upon 8C3. Now this will cancel. So it is 1, and this is 9, 8, 7. This is 3 into 2. Now this is 3. This is 4. 12. 12 into 7 is 1 by 84. Now we'll come to this third case when we have Mr. A's number should be larger than Mr. B's number. Now there are two cases. Case 1, if Mr. A's number start with 9. So if Mr. A's number starts with 9, then in that case it will always be greater than that of B's number, and this we have already calculated in part 1. So in this case, this probability that Mr. A's number will be 9, this is 1 by 3. Now if we consider the second case when Mr. A's number doesn't start with 9. Now here we have three cases. Case 1, either A's number will be greater than B's number, or both of them they choose the same number, or B's number will be greater than A's number. From symmetry we can say that number of elements in this first case will be same as number of elements in this second case. Now the probability that they'll choose the same number provided the number doesn't start with 9, it will be this 1 by 56, because we have not yet taken the case 2 by 3. So it will be this 1 by 56. So the probability that A chooses a number greater than B, provided A's number doesn't start with 9, it will be 1 minus 1 by 56 divided by 2, because we have equal number of elements in both the cases. Now it will be 55 divided by 112. Now this number is greater than 9 when A doesn't choose 9. So the probability that A chooses a number greater than B, if it is not 9, it will be this probability of not choosing 9, which is 2 by 3 into 55 by 112. Now this is 56, that will be 55, 8, 168. Now combining the two probabilities, we get our result that probability A's number will be greater than B will be 1 by 3 plus 55 by 168, and it will be 37 by 56, and that's your option A. So the correct options are B, C, and A. Now here the question is, let A1, A2, A3, A21 be the 21 vertices of a regular polygon of 21 sides inscribed in a circle with center O. So we have this circle with center O, and then we have these 21 vertices inscribed. So it is A1, A2, A3 up to A21, and they are all vertices of a regular polygon. Now triangles are formed by joining vertices of this regular polygon. Now total number of triangles that can be formed, it is given by 21C3, and 21C3 is 21 into 20 into 90 divided by 3 into 2. Now this is 7 and this is 10, so it will be 1330. So total number of triangles that can be formed is 1330. Now we need to find the probability that chosen triangle is equilateral triangle. So this first question is that the chosen triangle is an equilateral triangle. Now it will be an equilateral triangle if number of vertices between the three chosen vertices is same. So that means in that case
x1 must be equal to x2 and it must be equal to x3. Now sum of all x1, x2, x3 will be 21 minus 3, 18, and since it is 3x1, so each of xi it must be 6. So we have this combination like a1, a8, a15, and we'll go all the way from a1 to a7, a7, a14, and a21. So altogether we have 7 cases in which an equilateral triangle is formed. So this required probability will be 7 upon 1330, which is basically 1 by 190, and that's your option C. Now we know that angle in a semicircle is 90 degrees. So if there is a right angle triangle, then one of the sides must be diameter of this circle. But since we have 21 vertices, that means if we choose any one vertex opposite to A1, there won't be any vertex. So there will be vertices on the either side of it. In this case, it is not possible to choose a right angle triangle. So probability of choosing a right angle triangle will be simply 0. Now we have to find the probability that chosen triangle is an acute angle triangle. Now what we'll do is we'll actually calculate an obtuse angle triangle and we'll find how many obtuse angle triangles are possible. Now if we choose one vertex, say A1, then there'll be 10 vertices here and 10 vertices here. Now number of obtuse angle triangle that can be formed having one of the vertices with A1, it will be 2 into 10C2, which is 90. Now we have 21 such vertices. So total number of obtuse angle triangles that can be formed will be 21 into 90 divided by 2. Why divided by 2? Because if we have one case where we have suppose A1, A2 and A7, then if we consider A7, there also we'll have this case when we'll have A1, A2 and A7. With A2 it is not possible because for A2, A1 and A7 they lie on the opposite side. So therefore we have to divide it by 2. So it will be this 21 into 45, which is 945. So now we can find number of acute angle triangles. So number of acute angle triangles will be 1330 minus 945. It will be simply 385. So this required probability that this triangle is acute will be given by 385 upon 1330, which is 11 by 38, and that's your option A. So the correct options are C, D and A, and that is the answer to this question. Now here the question is, 3 randomly chosen non-negative integers x, y and z are found to satisfy the equation x plus y plus z equals 10. Then the probability that z is even is. Now first we have to find number of total ways of choosing x, y and z. Now this is nothing but this is number of non-negative integral solutions. Non-negative integral solutions for this equation. Now number of non-negative integral solutions for this equation is given by n plus r minus 1 c r minus 1, which is nothing but which is 12c2, and 12c2 is 66. So there are 66 ways to choose the values of x, y and z. Now we have to find our favorable case in which z is an even number. Now if z is even, we'll say let z is of the form 2k, where the value of k varies from 0 to 5. So we can write x plus y equals 10 minus 2k. Now if we find number of non-negative integral solutions is given by n
plus R minus 1, C R minus 1, which in this case will be 11 minus 2k C1, and that is 11 minus 2k. Now, these solutions, they vary from range 1 to 5. So, total number of favorable cases will be given by this summation. K varies from 0 to 5 Sk, and will be this summation. K varies from 0 to 5 11 minus 2k. Now, this is 11 plus 9 plus 7 plus 5 plus 3 and plus 1, which is sum of first 6 odd natural numbers, and sum of first 6 odd natural numbers is simply 6 square, which is 36. So this required probability will be 36 divided by 66, which is 6 by 11, option B. Now the question is 12 identical balls are to be placed in 3 identical boxes. Find the probability that one of the boxes contains exactly 3 balls. Since the balls and boxes, they are identical, it's just a problem of partitioning. So we have to partition this 12 in 3 parts. Now it can be done as 12 0 0 or 11 1 0 or 10 2 0 or 10 1 1, 9 3 0, 9 2 1, 8 4 0, 8 3 1, 8 2 2, 7 5 0, 7 3 2, 7 4 1, 6 6 0, 6 1 5, 6 2 4 and 6 3 3. Now with 5 it will be 5 5 2, there will be 5 4 3, and finally will be this 4 4 and 4. So altogether we have 9 and 10, 19 cases. So there will be these 19 cases in which we can distribute these 12 identical balls in 3 identical boxes. Now we have to find the probability that one of the boxes contains exactly 3 balls. Now here we have 3, here we have 3, here also we have 3, here we have 3, and here also we have 3. Now this language is not exactly clear. Now when it says one of the boxes contains exactly 3 balls, so does that mean out of the 3 boxes there is only one which contains exactly 3? So if that is the case, then we'll discard this. So this probability will be 4 by 19 if 2 boxes cannot have 3 3, and if it is 3 balls in at least one of the boxes, then in that case this probability will be 5 by 19, and it doesn't match any of the options. This question, it should not be 12 identical balls in 3 identical boxes. So what else it could be? Now we can take 12 identical balls in 3 distinct boxes. Now suppose we have 3 boxes, box 1, box 2 and box 3. Suppose we have x1, x2 and x3 number of balls in this. Then here we'll have x1 plus x2 plus x3. It must be equal to 12. So total number of ways of distributing these 12 balls in 3 distinct boxes will be n plus r minus 1 c r minus 1, and that will be 14 c2, which is 91. So that's our total cases. Now we have to find the favorable cases in which one of the boxes contains exactly 3 balls. Now suppose x1 is 3. Now if x1 is 3, then we get x2 plus x3 equals 9. Now solution to this is 9 plus 2 minus 1, c 2 minus 1, which is simply 10. Now in these 10 cases, we have this one case when he'll be this 3, 3 and 6, and this one case when he'll be 3, 6 and 3. So what we'll do is we'll discard these two cases. So then we have 8. So it'll be 8 cases when x1 is 3. In the same way, for x2 equals 3, we'll have 8 cases. And for x3 equals 3, we'll again have 8 cases. So this required probability when exactly one of the box contains 3 balls, it will be 24 by 91. But if the question is at least one of the box contains exactly 3 balls, then in that case, we have to include all these 6 cases. And in these 6 cases, 3 of them, they are repetitions. So in that case, this probability will be 24 plus 3, 27 by 91. So this is also noted. Now if it is 12 distinct in 3 identical boxes, then it's a distribution problem, which is very lengthy to calculate. So I won't calculate that one. So now I'll consider this case when we have 12 distinct balls which are to be placed in 3 distinct boxes. So now we have 12 distinct balls which are to be placed in 3 distinct boxes. Now for each ball we have 3 choices. So total number of ways of distributing these 12 balls in 3 boxes will be 3 into 3 into 3, 12 times, and there will be 3 to the power 12. Now the condition is one of the box contains exactly 3 balls. Now first we'll calculate which box contains these 3 balls. So it will be 3C1. Now in this box we have to select 3 balls from 12 distinct balls, which can be done in 12C 3 ways. Now we are left with 9 balls and 2 boxes. Now these 9 balls, they are to be distributed in these 2 boxes. Now if we consider the case when at least one of the boxes has 3 balls, then for each of the 9 balls we have 2 choices. So it can be distributed in remaining 2 boxes to the power 9 ways. So in this case, this required probability will be 3 and then 12, 11, 10, 3 to the power 9 upon 3 to the power 12. Now this 3 will cancel. This is 5. Now this is 3 to the power 11 and this is 2 to the power 11. So we'll write this as 55 into 2 by 3 to the power 11, which again doesn't match with any option. Another question is exactly one of them should contain 3 balls. In that case, from these 2 to the power 9 cases, we have to remove all those cases in which we have distributed them as 3 and 6. Now we can write this as factorial 9, factorial 3, factorial 6, and then it will be multiplied with factorial 2. In that case, this probability will be 3C1 into 12C3 to the power 9 minus 2 into 9C3 divided by 3 to the power 12. Now here the question is, there are 8 seats in the front row of a theatre in which 4 persons are to be seated. Then the probability of seating them so that no 2 persons are side by side. Now for this we need to select 4 chairs which are separate from each other. So basically this is nothing but this is non-consecutive selection. Now we have already studied non-consecutive selections in a row in one of the previous videos, and we know that if we have n objects and out of which we have to select k objects which are not constitutive. Then it can be done in n minus k plus 1 c k ways. Now in this, value of n is 8 and value of k is 4. So total number of ways of choosing 4 seats, so that none of them is side by side. It will be given by 8 minus 4 plus 1 c4, which is basically 5c4. So we can select these 4 non-constitutive seats in 5 ways. Now in these selected 4 seats, these 4 people, they can be arranged in factorial 4 ways. Now we need to find this probability. So it will be this 5 into factorial 4 divided by total number of ways. Total number is any 4 out of 8 into factorial 4. Now this factorial 4 will cancel. So this is 5 and this is 8, 7, 6, 5 and this is 4, 3, 2 and 1. Now 5 and 5 will cancel. Now this is 8. So this value is simply 1 by 14. So the probability that no two persons sit side by side is 1 by 14, and that's your option A. Now the next one is each person has exactly one neighbor. Now when each person has exactly one neighbor, that means 2 of them, they are sitting together. Another 2, they are sitting together, and in between them there should be at least 1. So suppose there are x1 seats here, x2 seats here and x3 seats here. So we write x1 plus x2 plus x3. It must be equal to 4, where x1 and x3, they are greater than or equal to 0 and x2 is greater than or equal to 1. Now we'll replace x2 with 1 plus x2 dash. So we can write this as x1 plus x2 dash plus x3. It is equal to 3, where each of xi or xi dash, it is greater than or equal to 0. That means we need to find number of non-negative integral solutions. So number of non-negative integral solutions is given by n plus r minus 1, and that is simply 10. Now we have 4 places here. Now in these 4 places, we can arrange these 4 people in factorial 4 ways, and then total number of ways of selecting these 2 and 2 seats will be 10 divided by total number of ways of arrangement, which is 8c4 into factorial 4. Now this factorial 4 will cancel. Now this is 10 and this is 8, 7, 6, 5 and this is 4, 3, 2, 1. Now 4 and this is 2. So this probability is nothing but simply 1 by 7, and that's your option C. Now this third part of the question is all of them sit together in a row, avoiding 2 end seats. So we have 8 seats, 1, 2, 3, 4, 5, 6, 7 and 8. So this is 1, 2, 3, 4, 5, 6, 7 and 8. Now we have to avoid this first seat and this 8th seat. Now all of them, they can sit in either 2, 3, 4, 5, 3, 4, 5, 6 and 4, 5, 6 and 7. So we have 3 choices, and then in the 4 consecutive, we can arrange them in factorial 4 ways divided by 8c4 into factorial 4. Now this factorial 4 will cancel. Now this is 3. Now this is 8, 7, 6, 5, 4, 3, 2, 1. Now this is 8. Now this is 2. So it will be this 3 by 70, and that's your option B. Now here the question is, A is a set containing n elements. A subset P is selected at random from set A, and set A is then reconstructed by replacing the elements. A subset Q is also chosen, may be void also. The probability that number of elements in P is equal to number of elements in Q. Now total number of ways of choosing P and Q will be, now for P we have 2 choices for each element, so there will be 2 into 2 into 2 n times, and for Q also it will be 2 into 2 into 2 n times. So total number of ways of choosing P and Q will be 4 to the power n. Now this first case is number of elements in P is equal to number of elements in Q. Either both of them, they'll have 0 elements or 1 element or 2 elements up to n elements. Now if they have both 0, then it will be nc0 square, both 1, nc1 square up to nc n square,
And from binomial, we know that this is nothing but this is 2n Cn. So this required probability will be 2n Cn divided by 4 to the power n, which is this option P. So this A, it matches with P. Now the second one is number of elements in P is more than that in Q. Now we'll have three cases. Either P will have more elements than Q, or they'll have same number of elements, or number of elements in P is less than number of elements in Q. Now there is no difference between the two sets and their conditions. That means number of elements in this case will be same as number of elements in the other case. So if we have to find this probability will be simply 1 by 2 and then 1 minus when they have equal number of elements, which is 2n Cn upon 4 to the power n. Now we can write this as 4 to the power n minus 2n Cn upon 2 to the power 2n plus 1, which is your option Q. So this B, it matches with Q. Now this third one is P intersection Q is 5. Now if P intersection Q is 5, then for each element we have three choices. Either it'll go to P, or it'll go to Q, or it won't go to any of P. So total number of ways of choosing two subsets P and Q such that their intersection is 5 will be 3 to the power n, and this probability will be 3 to the power n divided by 4 to the power n, which is your option S. So this C, it matches with S. Now D is Q is a subset of P. Now if Q is a subset of P, then first case is when Q doesn't have any element. So it is NC0. Then in that case, for each element, we have two choices. So we can construct this P in 2 to the power n ways. Now if there is one element in Q, now that element is already present in P, then for the remaining n minus 1 elements, we'll have 2 to the power n minus 1 choices. And then it will be NC2, 2 to the power of n minus 2, and then it will be NCn, 2 to the power 0, which is nothing but, which is binomial expansion of 3 to the power n. So favorable cases where Q is a subset of P is 3 to the power n. That means this required probability will be 3 to the power n upon 4 to the power n. So this D, it also matches with S. So A matches with P, B with Q, C with S, and D with S. And that is the answer to this question. Now here the question is, suppose there are 8 white and 2 red balls in a pocket. Each time one ball is drawn and replaced by a white ball. The probability of drawing out all the red balls just in the fourth draw is. So we have to find this probability that all the red balls are drawn in fourth draw. Now it should be just in fourth draw. That means this fourth draw, it must end in red. Now this first red, it can either be this first, second or third. So the possibilities are either it could be this R, W, WR, or WR, WR, or WW, R and R. So these are the three possibilities in which both the red balls, they are drawn in fourth draw. Now, probability of getting a red ball in this first part will be simply 2 by 10. Now, probability of getting a white ball. Now, since first ball is red, it's being replaced with white. So now we have 9 white and 1 red. So it will be this 9 by 10 into 9 by 10 into 1 by 10. Now here, first one is white. So it will be this 8 by 10. Now second one is red, so it will be this 2 by 10. Now we'll have 9 white and 1 red, so it will be this 9 by 10 into 1 by 10. Now this white is 8 by 10 into 8 by 10. Now here it is 2 by 10 and here it is 1 by 10. So this required probability will be this 9 into 9 into 2, that is 81 into 2. Plus 72 into 2 plus 64 into 2 divided by
1 0 0 0. Now this is 434 divided by 1 0 0 0, which is nothing but 0.0434, and that's your option B. Now here the question is, 4 dice are thrown simultaneously. It is given that 4 and 2 has appeared on any two of them. We need to find the probability that 3 has appeared on the remaining dice. Now this is conditional probability problem. Now suppose this is this event B, that from this 4 dice we have 4 and 2, and then this is this event A, which is probability that 3 has appeared on the remaining die. Now we need to find this conditional probability of A by B. Now this is probability of A intersection B upon probability of B. Now first we'll calculate probability of B, and probability of B is actually the probability that when we have thrown 4 dice, then 4 and 2, they have appeared in any two of them. Now we can solve this using inclusion exclusion. Now total number of ways, which is 6 to the power 4 minus all those cases in which at least one of them is missing. So if 4 is missing, then it'll be this 5 to the power 4, and if 2 is missing, it'll be this 5 to the power 4 minus this case when both of them they are missing, because this case is included twice. So there'll be this minus 4 to the power 4. So this required probability will be 6 to the power 4 minus 2 into 5 to the power 4 plus 4 to the power 4 whole divided by total number of ways is 6 to the power 4. Now this is 302 upon 6 to the power 4. So the probability that both 4 and 2 they'll appear will be this 302 upon 6 to the power 4. Now we'll find this probability of A intersection B. Now this A intersection B, we have a 4, we have a 2, and then we have 2 3s. Now in this case, out of these 4 dice, we need to select 2 dice for these 3 and 3. So out of these 4, we can select any 2 in 4C 2 ways. Now the remaining 2 dice, we can distribute 4 and 2 in factorial 2 ways. So that will be 4C2 into factorial 2 divided by 6 to the power 4. Now 4C2 is 12 upon 6 to the power 4. So this conditional probability will be simply 12 upon 302, which is 6 upon 351, and that's your option D. Now here the question is, let omega be a complex cube root of unity with omega unequal to 1. A fair die is thrown 3 times. If R1, R2 and R3 are the numbers obtained on the die, then the probability that omega to the power R1 plus omega to the power R2 plus omega to the power R3 is 0. Now we know that 1 plus omega square, it is 0. So we'll get 1 when the value of R is either 3 or 6. We'll get omega if it is either 1 or 4, and we'll get omega square if it is either 2 or 5. So that means for R1, R2 and R3, we have to choose one number from this set, one number from this other set, and one number from this third set. So from this first one, we can choose one number in 2C1 ways. For second, it will be 2C1, and for third, it is 2C1. Now once we have 3 numbers, they can be distributed in R1, R2 and R3 in factorial 3 ways. So it will be this factorial 3 divided by now total number of ways, which is 6 into 6 into 6. Now this factorial 3 will cancel. This probability will be simply 2 by 9, and that's your option C. Now here the first question is, 2 squares are chosen at random on a chessboard. Find the probability that they will have a side in common. Now, two squares will have side in common when they are either horizontally together or when they are vertically together. Now, for this case, we need two connected horizontal squares. Now, we have 8 rows. So, on these 8 rows, we can choose any one row. It is 8C1. And on any one row, we have to select two consecutive squares out of 8 consecutive. And number of consecutive selections is n minus r plus 1. In the same way, from 8 vertical, we can choose any one in 8C1 ways. And again, from 8 squares, 2 connected can be done in 8 minus 2 plus 1. So total case will be this into 2 divided by 64C2. Now this is 8 into 7 into 2, and this is 64 into 63 into 2. Now this is 8, 4, this is 2, and 7, 9. So this probability will be simply 1 by 18. So the probability that they have a side in common is 1 by 18, and that's your option 3. Now the second one is 3 squares of normal chessboard are chosen. Find the probability of getting 2 squares of one color and 1 square of different color. So we have two cases. Either it could be 2 black, 1 white, or 2 white and 1 black. Now total number of choices is 64, C3. Now 2 black, so it will be 32 C2, and 1 white is 32 C1, and it will be same for 2 white and 1 black, so it will be this into 2. Now we can write this as 32 into 31 divided by 2 into 32 into 2, and here it will be this 64, 63, 62, and this is 3, 2, 1. Now this 2 and 2 will cancel. Now 32 into 2, it is 64. Now this 3 is 21, 31 into 2. Now this is 16. So this probability will be 16 by 21, and that's your option 1. Now this third case is 3 squares are chosen at random. The probability that 2 are of one color. Now 2 of one color and 1 of different color. I think it's the same question, so we'll discard it. And then finally we have 4 squares are chosen at random from a chessboard. We need to find the probability that they lie on a diagonal line. So if we look at diagonal lines, so here we have 1, 2, 3 and 4. We have to choose 4 on a diagonal. So it could be this 4C4 plus 5C4 up to 7C4 and then 8C4. And after 8C4, again we'll have 7, 6, 5 and 4. So it'll be this into 2 and whole divided by 64 C4. Now we can also choose diagonal the other way. So this total case will be this 2 into this value. So we can write this as 4 into this summation n C4, where n varies from 4 to 7, and plus 2 into 8C4 divided by 64C4, and that's your option 4.
Now here the question is, 3 vertices are chosen at random from the vertices of a regular hexagon. If P1, P2 and P3 are probabilities that triangle formed by 3 vertices is right angle, obtuse and acute angle, then which of the following is true? So we have this hexagon having 6 vertices. Now P1 is the probability that triangle formed by selected 3 vertices is a right angle triangle. Now if we select this vertex, then it'll be right angle triangle if we choose either this vertex or this vertex. So there will be two triangles possible for any given vertex. So what we'll do is first we will find total number of triangles that can be formed. Total number of triangles that can be formed is simply 6C3 and 6C3 is 20. Now in the first case, we need to find number of right angle triangles. Now number of right angle triangles is, first we choose any one vertex and it can be done in 6C1 ways. And once we choose any one vertex, then in order to form a right angle triangle, we have choice of two vertices. So they'll be into 2. So this required probability will be simply 12 by 20 or 3 by 5. So value of P1 is 3 by 5. Now we have the second case when it says triangle formed is an obtuse angle triangle. Now again, if we choose this vertex, then it will be an obtuse angle triangle if we choose either this vertex or this vertex. Now if we look at obtuse angle triangle, then we can get obtuse angle triangle if and only if these three vertices they are consecutive. If the three vertices they are consecutive, then in that case we'll get an obtuse angle triangle. Now we have already studied in consecutive selection along a circle that if there are n points and we have to choose r consecutive points, it can be done in n ways. So number of obtuse triangles will be simply 6. So this probability P2, first one's P1, will be simply 6 by 20, which is 3 by 10. Now this is 0.6 and this is 0.3. Now we'll get an acute angle triangle only if we choose a triangle so that none of the side is the side of hexagon. Now in this case we have only two possibilities. So this P3 will be simply 2 by 20 and there will be simply 0.1. Now clearly P3 it is less than P2 and P2 is less than P1. So P1 is greater than P2 is greater than P3 and that's your option D. And if we look at this option C, which is P2 plus 3P3. Now P2 is 0.3 and 3 times P3 is also 0.3. So this is 0.6 and it will be equal to P1. So this option C is also correct. So the correct options are D and C. Now here the question is, if P and Q are chosen randomly from the set 1, 2, 3 up to 10 with replacement, then the probability that roots of this equation are real, imaginary, real and equal, and real and distinct is. Now discriminant for this quadratic equation will be P square minus 4Q. Now if we consider this first case when discriminant is equal to 0, that is when the roots are real and equal, in that case we'll have P square equals 4Q, or we'll get P as 2 under root Q. Now in this, Q has to be a perfect square. So in this case, the values of Q which are possible is Q can be 1, Q can be 4 and Q can be 9. Now if we take Q as 1, we'll get P as 2. If we take Q as 4, we'll get P as 4. And if we take Q as 9, we'll get P as 6. So these are the three cases possible. So this required probability that they are real and equal will be this 3 divided by total number of ways. Now for P we have 10 choices and for Q we have 10 choices. So that will be this 3 by 100 and that's your option C. Now if we take the second case when D is greater than 0, which means this P square minus 4Q it should be greater than 0 or Q is less than P square by 4. Now what are the possible options for P and Q? Now if P is 1, Q is less than 1 by 4, no option. If P is 2, Q is less than 1, again no option. So the smallest one will be P equals 3. Now if P is 3,
Q is less than 9 by 4, and 9 by 4 is 2 point something. So value of Q is either 1 or 2. So we have two cases here. Now if P is 4, now it will be the 16 by 4 is 4. So the Q can take the values 1, 2 and 3. So there will be 3 cases here. If we take P as 5, now 25 divided by 4, there will be 6 point something. So Q can take the value from 1 to 6. So we have 6 phase. If P is 6, there will be Q is less than 9. So you take the value from 1 to 8. If P is 7, there will be 49 by 4 is 12 point something. So here you can take values from 1 to 10. So for all the values of P from 7, 8, 9 and 10, you can take all these 10 values. So here for these 4 cases, total values we have is 40. Now if we add them, we'll get this as 59. So the probability that roots are real and distinct will be this 59 by 100. That means option D is incorrect. Now roots are real when they are either real and equal or real and distinct. So this probability that roots are real will be this 59 plus 3, which is 62. 62 divided by 100, and that will be 31 by 50. So this option A, it is incorrect. Now they'll be imaginary if they are non-real. So it will be 1 minus 31 by 50, and that will be 19 by 50. That means option B is correct. So the correct options are B and C. Now here the question is, out of 2n plus 1 tickets consecutively numbered, 3 are drawn at random. The chances that the numbers are in AP is. Now if we find total number of ways of choosing 3 tickets, it will be 2n plus 1 C3, and these 3 tickets, they are in AP, and for this AP we have worked out a formula which I have discussed in the compendium, and the formula is, it is n minus 1 whole square by 4 if n is odd, and it is n into n minus 2 by 4 if n is an even number. Now in this case we have odd number of tickets, so here this favorable case will be 2n plus 1 minus 1 whole square upon 4. So it will be simply this n square. So this required probability will be n square upon 2n plus 1 C3. Now this is n square, and this is 2n plus 1 into 2n minus 1, and here it is 6. Now this n will cancel, it will be this 3. So we can write this as 3n upon 4 n square minus 1, and there will be your option 3. That says there are 6 red balls and 6 green balls in a bag. 5 balls are drawn out at random and placed in a red box. Remaining 7 balls are put in a green box. If the probability that number of red balls in green box plus the number of green balls in the red box is not a prime number is P by Q, where P and Q are relatively prime, find the value of P plus Q. So initially we have 6 red and 6 green balls. Now from this we have drawn 5 balls, and we have put those 5 balls in the red box, and then remaining 7 balls, they are put in green box. Now it says if the probability that number of red balls in green box, so suppose number of red balls in green box is R and number of green balls in red box is G. So in red box we have G green and 5 minus G red, whereas in green box we have R red and 7 minus R green balls. Now if we count total number of red balls, it will be 5 minus G plus R, and it'll be equal to 6. And total number of green balls, there'll be G plus 7 minus R, and it should be equal to 6. So from here we can write value of R minus G, it should be 1. So that is the relationship between R and G. Now it is also given that R plus G, it is not a prime number. Now we need to find possible values of R and G. Now clearly G must be less than or equal to 5 and greater than 0, and R must be less than or equal to 7 and it must be greater than 0. Now we look at various combinations of R and G. Now R could be 1 and G could be 0. Now in this case, R minus G is 1 and R plus G is not a prime number. So we're going to select it. It could be 2, 1 and 2 plus 1 is 3. We are not going to accept it. Now 3, 2, it is also prime. 4, 3, also prime. 5 plus 4, 9, it is possible. And then 6, 5. 6 plus 5 is 11. So out of these 6 cases, there are only 2 cases where this R plus G it is not a prime number. Now we need to find this probability and it is given as P by Q. Now for this red, we need to choose 5 balls. So out of 12, we can choose any 5. So it will be 12C5. And the first case, we have 1 red and 0 green. So from this, it will be 6C1 into 6C0 plus here it is 6C5 into 6C4. So this probability will be 6 plus 6 into 15 upon 12, 11, 10, 9, 8, 5, 4, 3, 2, 1. Now 4 into 3 is 12, 5 into 2 is 10. Now this value is 6 into 16 upon 11 into 9 into 8. Now this is 2. So it will be this 12 upon 99, which is 4 by 33. So in this case, value of P is 4 and value of Q is 33. Now we need to find the value of P plus Q. Now P plus Q in this case is 37 and that is the answer to this question. Now here the question is, a mapping is selected at random from a set of all mappings of the set A 1, 2, 3, 4 to itself. The probability that mapping selected is a bijection. Now total number of mapping. For each element we have 4 choices. So there will be 4 into 4 into 4, 4 times. So it will be 4 to the power 4. Now if it is a bijection, then it will be a 1, 1 function. So we have to arrange these 4 against the permutations of these 4, and which is done in factorial 4 ways. So this probability is factorial 4 upon 4 to the power 4 or factorial 3 upon 4 cube, and that's your option 3. Now here the question is, 3 unbiased dice are rolled and the numbers on them are noted as A, B and C. The probability that the planes intersect along a line, intersect at one point, form a triangular prism is. Now if we look at these 3 equations, all these 3 equations, they are homogeneous equations. And if they are homogeneous equations, that means either it will have a unique solution or it will have infinitely many solutions. That means these 3 planes, they can never form a triangular prism. So the probability that they form a triangular prism is going to be 0. So that means this option C, it is correct. Now if we look at delta for these homogeneous equations, this delta will be this A, B, C, B, C, A and C, A, B. We know that we'll get this as 1 by 2 and then A plus B plus C will be A minus B square plus B minus C square plus C minus A whole square. And if it is equal to 0, we'll have infinitely many solutions.
And if it is unequal to 0, then we have a unique solution. Now clearly this a plus b plus c, it can never be 0. So this delta, it can only be 0 if and only if a equals b equals c. Now if a, b, c, they are all equal, in that case all the three planes, they'll be representing the same plane. So in that case also they won't intersect in a line. All the three planes, they'll be identical planes. So that means this option A, it is incorrect. And for all the other cases except for a equals b equals c, we'll get this condition that this delta is unequal to 0. Now this probability, it will be 6 into 6 into 6 minus those 6 cases when all a, b, c, they're equal, divided by 6 into 6 into 6. Now this is 210 divided by 216. If we divide by 2, we'll get 105 upon 108, and that's your option B. Option D is incorrect. So the correct options are B and C. Actually, we can further reduce this 105 upon 108. If we divide it with 3, we'll get this as 35, and here will be this. So it should be 35 by 36. Now here the question is, 3 6-faced square die are thrown together. Let pk denote the probability that sum of numbers appearing on dice is k, and if this summation k varies from 9 to 14, pk, then find the value of 54s minus 30. Now suppose number on first die is x1, number on second die is x2, and number on third die is x3, and it must be equal to k, where each of xi, it can take the value from 1 to 6. Now since for each x we have a minimum and a maximum, so what we'll do is we'll solve this question using binomial theorem. So that means we have to find coefficient of x to the power k in the expansion of x plus x square up to x6, and since we have 3 dice, so it will be this power 3. Now we can take x cube common, so basically we can write, we have to find coefficient of x to the power k minus 3 in the expansion of 1 plus x square up to x to the power 5 to the power 3, or we can write coefficient of x to the power k minus 3 in the expansion of 1 minus x to the power 6 upon 1 minus x whole cube, which is coefficient of x to the power k minus 3 in 1 minus x to the power 6 to the power 3 into 1 minus x to the power minus 3. Now value of k, it lies from 9 to 14. Now k minus 3 is 6 up to 11. So this power, it goes from 6 to 11. So we can write this as, we need to find coefficient of x to the power k minus 3 in 1 minus 3x to the power 6, and we'll discard higher powers into 1 minus x to the power minus 3. Now we know that coefficient of x to the power r in the expansion of 1 minus x to the power minus 3 will be n plus r minus 1 CR. So there will be 3 plus r minus 1 CR, or we can write this as r plus 2 C2. So it will be this coefficient of x to the power k minus 3 in 1 minus 3 into x to the power 6, and then this binomial summation of r plus 2 C2 x to the power r. Now we get coefficient of x to the power k minus 3 if we take r as k minus 3. So it will be this k minus 3 plus 2 C2 and then minus 3 into now x to the power 6 into x minus r. So it will be coefficient of k minus 9. So there will be k minus 9 plus 2 C2. So sum of the numbers will be k in k minus 1 C2 minus 3 into k minus 7 C2 ways. Now we need to find this probability that this sum is k. So this probability will be given by k minus 1 C2 minus 3 into k minus 7 C2 divided by total choices, and that will be 6 into 6 into 6, and that is 216. Now we need to find this S, which is this summation k varies from 9 to 14 pk, and which will be this summation k minus 1 C2 where k varies from 9 to 14 minus 3 times this summation k varies from 9 to 14 k minus 7 C2 divided by 216. Now we need to solve these two summations. Now if we look at this summation, which is summation k minus 1 C2 where k varies from 9 to 14, basically it will be this 8C2 plus 9C2 up to 13C2. Now what we'll do is we'll add 8C3 and we'll subtract 8C3. Now and same r differs by 1, so it'll be this 9C3, again 9C2 plus 9C3 will be 10C3, and finally it'll be 13C2 plus 13C3, and that'll be 14C3. So this value will be 14C3 minus 8C3. And if we look at the second series, which is this summation k varies from 9 to 14 k minus 7C2. Now this is 2C2 plus 3C2 up to 7C2. Now 2C2 is 1. We can also write this as 3C3. So next one will be 4C3, and finally will be 8C3. So this first summation is 14C3 minus 8C3, and this second summation is 8C3. Now we put the values of these summation, then we can write this S as 14C3 minus 8C3 and minus 3 8C3. So that will be 4 into 8C3 divided by 216. Now 14C3 is 14 into 13 into 12, and this is 6 minus 4. Now this is 8, 7, 6, and this is 6 divided by 216. Now this is 2 and this is 6. So it will be this 28 into 13 minus 8. 13 minus 8 is 5 divided by 216. Now this is 7, 54. So it will be this 35 by 54. So value of S is 35 by 54. Now we need to find the value of 54S minus 30. Now 54S minus 30, and there will be 35 minus 30, which is simply 5. So answer to this question is 5. Now the question is, consider the system of equations AX plus BY equals 0 and CX plus DY equals 0, where ABCD, they take the value either 0 or 1. So what are the total number of ways in which we can define ABCD? So for each we have two options. So total number of ways to define these equations will be 2 into 2 into 2 4 times, and that will be 16. Now statement 1 is probability that
system of equation has a unique solution is 3 by 8 and statement 2 is the probability that system of equation has a solution is 1. Now since this is a homogeneous equation, it will always have a trivial solution. So x equal to 0 and y equal to 0 will always be one of the solutions. So this system of equation will always have a solution and therefore it is a sure event. That means this statement 2 is correct. Now for the statement 1, we have to check the condition that the system of equation has unique solution. Now homogeneous equations will have unique solution if their determinant a, b, c, d, it is unequal to 0. That means AD minus BC, it is unequal to 0. Now it will be unequal to 0 when one of them is 1 and another one is 0. So we have this first case when AD is 1 and BC is 0, and this second case when AD is 0 and BC is 1. Now if AD is 1, then A should be 1 and D should be 1. Now if B into C is 0, we can have B0 C1, C0 B1, or B equals to 0 and C equals 0. Now here we have B into C as 1, so B should be 1 and C should be 1, and here we'll have either A0 D1, D0 A1, or both of them 0. So altogether we have 6 cases when the value of this determinant is non-zero. So this required probability will be 6 by 16, which is 3 by 8. That means the statement 1 is correct. So statement 1 is correct and statement 2 is correct, and we have not used any part of statement 2 to prove statement 1. So that means statement 2 does not explain statement 1. Now here the question is, 3 6-faced fair dice are thrown together. The probability that sum of numbers appearing on dice is k. That means we have to find coefficient of x to the power k in the expansion of x plus x square up to x to the power 6, and together there are 3 fair dice. So it will be this 3. Now we can take x cube common, so we can find coefficient of x to the power k minus 3 in the expansion of 1 minus x to the power 6 to the power 3 into 1 minus x to the power minus 3. Now since k minus 3 it is less than 6, so that means we simply have to find coefficient of x to the power k minus 3 in the expansion of 1 minus x to the power minus 3. Now coefficient of x to the power r in the expansion of 1 minus x to the power minus n, it is given by n plus r minus 1 cr. So it will be this k minus 1 c2, which is k minus 1 into k minus 2 whole divided by 2, and that's your favorable cases. Now total number of cases will be 6 into 6 into 6. So this required probability will be k minus 1 into k minus 2 divided by 2 into 216, which is k minus 1, k minus 2 and 432. That's your option A. Now here the question is, from 2n plus 1 consecutive positive integers, 3 are selected at random. The probability that they are in AP is 3n upon 4n square minus 1, and from 2n consecutive positive integers, 3 are selected at random. The probability that numbers of them are in AP is 3 upon 2 into 2n minus 1. Now in one of the previous videos in permutations and combinations, we have already studied that if we have to choose 3 numbers in AP from n consecutive integers, then it will be 1 by 4 n minus 1 whole square if n is odd, and it will be 1 by 4 into n minus 2 if n is even. Now for the first one, if we have to select 3 numbers in AP, now in this case 2n plus 1, it is an odd number, so this
required probability for this first case, it will be 1 by 4. Now n in this case is 2n plus 1. So it will be 2n plus 1 minus 1 whole square divided by total number of ways of selecting 3 from 2n plus 1. So it will be 2n plus 1 C3. Now this 3 and 3 will cancel. So we'll get this as n square upon, now this is 2n plus 1, 2n, 2n minus 1, and here it is this 6. Now n and n will cancel. Now this is 3. So this value will be 3n upon 4n square minus 1, which is our first result. Now for the second one, we have even number of numbers. Now in this case, this probability will be, now favorable cases, it is 1 by 4 n into n minus 2 if n is even. So it will be this 1 by 4, n in this case is 2n into 2n minus 2 divided by any 3 from 2n. So it will be 2n C3. So we'll write this as 1 by 4, 2n, 2n minus 2, and this is 2n, 2n minus 1, 2n minus 2 into 6. Now I'll cancel. This value will be 3 upon 2 into 2n minus 1, which is our second result. So this is the answer to this question.
Today we'll discuss CMI's 2017 paper, and the first question is, positive integers a and b, possibly equal, are chosen randomly from among the divisors of 400. The numbers a and b are chosen independently, each divisor being equally likely to be chosen. We need to find the probability that GCD of AB is 1 and LCM of AB is 400. Now first we look at number of divisors of 400. Now we know that 400 is 25 into 16. So there will be 2 to the power 4 into 5 square. So we know that if we have any number n which is expressed as prime powers like p1 to the power a, p2 to the power b, p3 to the power c, number of divisors is given by a plus 1, b plus 1, c plus 1, and so on. So in the case of n100, number of divisors in the case of 400 is 4 plus 1, which is 5, and then 2 plus 1, which is 3. So in total we have 15 divisors of 400. Now it says two positive integers a and b are chosen from these 15 divisors and they can be possibly equal. So that means we can choose one number more than once. So we'll find total number of choices for AB. So total number of choices for A and B will be, so first we look at total number of choices for A. We have 15 choices for A, and the same way we have 15 choices for B. So altogether we have 225 choices. Now we need to find this probability that these numbers are chosen such that their GCD is 1. That means there is nothing common between A and B, and LCM of AB is 400. This simply means that A and B are coprime factors of this number n. So we are looking for coprime factors. Now how do we split 400, which is 2 to the power 4 into 5 square, in two coprime factors? So for coprime factors we know that each of these terms 2 to the power 4 and 5 square, they must go to either A or B. So that means for this 2 to the power 4 we have two choices, either it will go to A or it will go to B. In the same way 5 square, again we have two choices, either A or B. So we have two choices for 2 to the power 4, we have two choices for 5 square. So total number of coprime factors is simply 4. If we want to write coprime factors, then we can write them also. Suppose we have A and B. Now A can be 1, B can be 2 to the power 4 into 5 square. This could be 2 to the power 4, B could be 5 square, or we can reverse them. It could be 5 square and 2 to the power 4, or it could be 2 to the power 4 into 5 square, and here B could be 1. So we have 4 possible ways in which we can split this number n into coprime factors. So this Required probability is favorable case, which is 4, upon total number of case, which is 225. So this probability is simply 4 upon 225. Now question number 5 is, you are given an 8 cross 8 chessboard. If two distinct squares are chosen uniformly at random, find the probability that two rooks placed on these squares attack each other. We know that a rook can move either horizontally or vertically in a straight line. So we have this 8 cross 8 chessboard, and we need to find the probability that these two rooks placed, they will attack each other. Now we need to find this probability. Suppose the event is A, so we need to find probability of this event A. Now first we'll find total number of ways in which we can place two rooks on these two squares. So altogether there are 64 squares, and from these 64 squares we need to select any two squares to place these two rooks. So it can be done in 64C two ways. Now we need to find the probability that these two rooks, they'll attack each other. So we know that these two rooks, they'll attack each other if they are placed on the same horizontal file or if they are placed on the same vertical file. So we'll take this case 1 when the two rooks are on same horizontal file. So we have 8 files. So from these 8 files, we can select any one file, and it can be done in 8C1 ways. Now once we have selected any file, then on this file, if we'll select any two squares, then these two rooks, they'll be attacking each other. So from these 8, we'll need to select any two squares, and it can be done 8C2 ways. Now plus, we can also place these rooks vertically. Now we'll have to place them vertically, then we'll have to choose a vertical file. So we have 8 vertical files. So from these 8, again we'll select any one. So it is 8C1. And again on this selected file, we can place these rooks on any two squares, and it can be done 8C2 ways. Now this is 8C1, which is 8. Now 8C2 is 8 into 7 divided by 2. So it will be 28 into 2, because both the values, they'll be same, upon 64 into 63 into 2. So 8, 864, 4, 4, 14, this is 2 and 9. So the probability that these two rooks will attack each other is simply 2 by 9. Now question number 14 is, there are 7 horses in a race. Mr. Murthy selects 2 horses at random and bets on them. What is the probability that Mr. Murthy selected the winning horse? Now total number of ways in which Murthy can select 2 horses is 7C2. Now we need to find this probability that he has selected the winning horse. That means one of the horse, it must be the winning horse, and then he can choose this other horse in 6C1 ways. So it will be simply 6, and then here will be 7 into 6 into 2, which is 2 by 7. So this required probability is 2 by 7, and that's your option B. Now question number 10 is, two numbers x and y are chosen at random from the set 1, 2, 3 up to 30. Then the probability that x square minus y square is divisible by 3 is. Now first we'll find total number of case. So total number of case will be 30C2. So from these 30 numbers, we can select any two numbers, and it will be given by 30 into 29 divided by 2. Now we have to find the probability that this x square minus y square is divisible by 3. So we can write x square minus y square as x minus y and x plus y. Now what we'll do is, we'll partition this set in 3 subsets. Set 1, which are multiple of 3. So it will be 3, 6, 9 up to 30. Then numbers which leave the remainder 1. So it will be 1, 4, 7. And then numbers which leave the remainder 2. So it will be 2, 5, 8 and such numbers. So there will be 10 elements in the first set, 10 elements in the second set, and 10 elements in the third set. Now this number x square minus y square, it will be divisible by 3 when either both the numbers, they belong to the same set. So either it can be from this first set or from the second one or from the third one. So it can be any of the set 3C1, and from this set we can select any two numbers in 10C2 ways. Or when x plus y is divisible by 3. Now x plus y will be divisible by 3 when either we choose elements from this set, so which we have already done in the first case, or when we choose one element from this set and another element from this second set. So it will be 10c1 into 10c1. So probability that this number is divisible by 3 is 3 into 10c2. Now 10c2 is 45 plus 100 upon 15 into 29. So it will be 3 and 9, 20. So it will be 47 upon 87, and that's your option number D. Now part B is there are 4 red, 5 black and 6 blue balls in an urn. So we have this urn. So here we have 4 red, 5 black and 6 blue balls. Now 4 balls are drawn at random without replacement from this urn. What is the probability that these 4 balls will contain at least one ball of each color? Now first we'll find total number of elements in sample space. So altogether we have 15 balls, and from these 15 balls we can select 4 balls in 15C 4 ways. Now we'll need to find number of favorable outcomes. Now the outcomes will be favorable when these 4 balls, they contain at least one ball of each color. So there will be 3 cases. Either it will have 2 red, 1 black and 1 blue, or 1 red, 2 black and 1 blue, or 1 red, 1 black and 2 blue. Now 2 red will be simply 4c2, 1 black 5c1 and 1 blue 6c1 plus 4c1, 5c2, 6c1 plus 4c1 into 5c1 into 6c2. Now 4c2 is 6, 5c1 is 5 and 6c1 is 6. Now 4c1 is 4, 5c2 is 10 and 6c1 is 6 plus 4c1 is 4, 5c1 is 5 and 6c2 is 15. We can take 60 common. So we'll take 60 common. We'll get 3 plus 4 plus 5. So it will be 12 into 60. Now this required probability will be number of favorable outcomes, which is 12 into 60 upon total outcomes, which is 15 C4, 15, 14, 13 and 12, and then 4, 3, 2 and 1. So 12 will cancel, 15, this is 4, 2 is 7, so it will be 48 upon 91. So the required probability is 48 by 91. Now here the question is, Mr. A lives at origin. So Mr. A lives at 0, 0 and he has his office at 4, 5. So his office is at 4, 5. His friend lives at 2, 3. So we have this friend living at 2, 3. Now Mr. A can go to his office traveling from one block at a time, either in plus y or plus x direction. If all possible paths are equally likely, then probability that Mr. A passed his friend's house is shortest path for any event must be considered. Now first we need to find total number of ways in which this man A, he can reach his office. Now in order to reach his office, he must travel 4 blocks in x direction and 5 blocks in y direction. So total number of ways will be total arrangements of 4 horizontal and 5 vertical blocks, and it is given by, now total is factorial 9, 4 horizontal are same and 5 vertical are same, so it will be this factorial 9 divided by factorial 4 factorial 5. So this is your total number of ways of reaching office. Now we have to find the cases when he reaches his office visiting his friend. Now first he needs to visit his friend. So this favorable will be, now we have 5, so it will be this factorial 5 divided by factorial 2 factorial 3, and here we have 2 and 2. So it will be factorial 4, factorial 2, factorial 2. So this required probability will be this favorable case, factorial 5, factorial 4. Now this is factorial 2, factorial 3, factorial 2, factorial 2 divided by this, which is factorial 9, factorial 4, factorial 5. Now this is factorial 4. This is 9, 8, 7, 6, and this is 4, 3, 2, 1. Now 2 will cancel. This is 4, and factorial 5 is 5, 4, 3, 2, 1. Now this 4 will cancel. This is 3, so we'll get this as 10 by 21, and that's your option B. So basically, it's a grid problem which we have already studied in permutations and combinations. Now here the question is, if f is a set of all onto functions from A to B. Now in this set A, we have n elements, A1, A2, An, and in this B, we have 3 elements which are X, Y, and Z. And f belongs to f is chosen randomly. What is the probability that f inverse x has 2 elements in it? And second part is f inverse x is a singleton. So basically here we are not talking about inverse function per se. Since it will be a many-one function, it cannot have inverse function defined for it. So basically what we are looking for is pre-images of x. So for the first part, it says this x has 2 pre-images, and for the second part it says it has only 1 pre-image. Now for this, first what we'll do is we'll find number of onto functions which can be defined from this set A to set B. So we have to find total number of functions that can be defined. So what we'll do is from total, we'll subtract all those cases in which at least one of the element is missing. So for each element, we have 3 choices. So total number of functions that can be defined from A to B, it will be 3 to the power n. Now minus this first case when x is missing. So it will be this 2 to the power n. For y is missing, again 2 to the power n. For z is missing, 2 to the power n. So it will be this 3 into 2 to the power n minus this case when 2 of them they are missing. If x, y is missing, all of them they go to z. So it will be this minus 3. So total number of onto functions from A to B will be given by 3 to the power n minus 3 into 2 to the power n plus 3. Now for this first one, now f inverse x has 2 elements in it. Now which 2? So from these n, we can select any 2 in NC 2 ways. Now these 2, they are mapped to x. Now remaining n minus 2 elements, they must be mapped to y and z, and it must be an onto function. So total number of functions is 2 to the power n minus 2 minus 2 cases when all of them they are either mapped to y or they are either mapped to z. So this required probability, it will be nc2 2 to the power of n minus 2 minus 2 divided by 3 to the power n minus 3 into 2 to the power n plus 3. And then the second case where this x has only 1 pre-image. So for the second part, we have to select 1 pre-image, it is nc1, and then for the remaining n minus 1 elements, we have to define an onto function from A to y and z. So it will be 2 to the power of n minus 1 minus 2. So this required probability will now be nc1 2 to the power of n minus 1 minus 2 upon 3 to the power n minus 3 into 2 to the power n plus 3. And that is the answer to this question. Now here the question is, if n integers are taken at random and they are multiplied together, show that the chances that last digit of the product is 1, 3, and it should be 7 also. 1, 3, 7 and 9 is 2 to the power n upon 5 to the power n. The chances of it being
2, 4, 6 and 8 is 4 to the power n minus 2 to the power n upon 5 to the power n. Its being 5 is 5 to the power n minus 4 to the power n upon 10 to the power n, and that of its being 0 is this value. Now we know that last digit on any number could be 1, 2, 3, 4, 5, 6, 7, 8, 9 or 0. Now we multiply any number with 2, 4, 6, 8 and 0. It will be an even number. We do not want that number to be even. And if we multiply it with 5, then it will either end with 0 or with 5. So that means we cannot choose 2, 4, 5, 6, 8 and 0. So the chances that last digit of the product is 1, 3, 7 and 9 if we choose the numbers whose last digits are 1, 3, 7 and 9. So that means this probability should be 4 by 10. Now it should be 4 by 10 for the second number, 4 by 10 for the third number, and it goes all the way up to 4 by 10 for all the n numbers. So this is nothing but this is 2 by 5 to the power n. So this first case when the last digit of the product is 1, 3, 7, 9 is 2 by 5 to the power n. Now the second one is chances of its being 2, 4, 6 or 8. Now if it is 2, 4, 6 or 8, then from these 10 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, it should not have 0. It should also not have 5, and it should have at least one of 2, 4, 6 or 8. So from these 8 numbers we can form 8 to the power n numbers, and from this we'll subtract all those cases in which none of 2, 4, 6 or 8 is chosen. So there will be 8 to the power n minus 4 to the power n divided by 10 to the power n. So this required probability will be 4 to the power n minus 2 to the power n upon 5 to the power n, and that's your second part. Now in the third part it says the probability of its being 5. Now it will be 5 when out of these 10, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. It should not have 0. It should not have any of these even numbers, and it must contain at least one 5. So total number that can be formed is 5 to the power n minus all those cases in which 5 is not included, 4 to the power n divided by 10 to the power n, and that's our third probability. And finally we have this where it says the probability of its being 0. Now basically all these 4 cases, they are mutually exclusive and exhaustive. So first we'll find sum of all these 3 probabilities. Now say it is P1. Now this is 2 by 5 to the power n, which is 4 to the power n. This one is 8 to the power n minus 4 to the power n, and this is 5 to the power n minus 4 to the power n upon 10 to the power n. Now here 4 to the power n will cancel. So the required probability is complement of this. So it will be 1 minus, and this is 8 to the power n plus 5 to the power n minus 4 to the power n upon 10 to the power n. So it will be this 10 to the power n minus 8 to the power n minus 5 to the power n plus 4 to the power n divided by 10 to the power n, and this is what we need to prove in this question. Now here the question is 7-digit numbers are formed using the digits 1, 2, 3, 4, 5, 6, 7, 8 and 9 without repetition. The probability of selecting a number such that product of any 5 consecutive digits is divisible by either 5 or 7 is P, then 12P is equal to. Now first we'll calculate total number of numbers that can be formed. Now total number of numbers that can be formed is simply 9C7, and then once we have these 7 digits, we can form these numbers in factorial 7 ways. So it will be this 36 into factorial 7, and that's our total number of ways. Now we'll calculate favorable number of cases, and for that
what we'll do is we'll take 3 scenarios. Case 1, when we have not included 5 and we have not included 7 in the 7 numbers. So if we have not included 5 or 7, then we are left with 7 numbers. So in that case, total number of numbers that can be formed is factorial 7, and all these numbers, they won't be divisible by either 5 or 7. Now we'll consider the second case when exactly one of 5 or 7 is included. Now in this case, which one? So from these two, we'll select one. So it'll be 2C1, and then from the remaining 7, we have to select 6. So there'll be 7C6. Now it's a 7-digit number: 1, 2, 3, 4, 5, 6, and 7. Now it says any 5 consecutive digits is divisible by either 5 or 7. Now if we take 5 consecutive, it'll be this from this side and it'll be this from the other side. Now if 5 or 7 they appear in the middle 3, then in that case those numbers will be either divisible by 5 or 7. Now we want the numbers which are not divisible by 5 or 7. So that means this 5 or 7, they must occupy a place from these 4 places. So for 5 we have to choose one place, and that can be done in 4C 1 ways, and then we can arrange these remaining 6 numbers in factorial 6 ways. So that's our second case when exactly one of 5 or 7 is included. So if there is no 5 and no 7, all the numbers are not divisible by 5 and 7. For second also, these are the cases where the number formed is not divisible by 5 or 7. We are solving this question using exclusion. And then this third case when both 5 or 7 are included. Now if both 5 and 7 are included, in that case, we already have 2 numbers. That means from the remaining 7, we have to select any 5. So there will be 7C5. Now the numbers formed by them must not be divisible by 5 or 7 for any 5 consecutive digits. So it can happen if number starts with 57, then we'll have 5 digits which are consecutive and not divisible by 5 or 7, or it can be 75, or it could be numbers ending with 57 or numbers ending with 75. Then there is this another possibility when number starts with 5 and ends with 7. So we have group of 5 which is not divisible, or is 7 and 5. So we'll have 6 cases in which we can position 5 and 7. So it will be this into 6, and then we can arrange these remaining 5 numbers in factorial 5 ways. So these are the possible cases where number formed is such that any 5 consecutive digits are not divisible by either 5 or 7. Now we'll calculate this probability using exclusion. So this probability will be 1 minus, now this is factorial 7 plus 2C1, 7C6, 4C1, factorial 6 plus 7C5 into 6 into factorial 5 divided by 36 factorial 7. Now this is 1 minus, now this is factorial 7. Now 7C6 is 7 and into factorial 6 is factorial 7, and this is 8. So it will be this 8 into factorial 7 and plus, now 6 into factorial 5 is factorial 6, and 7C5 is 7C2, and 7C2 is 7 into 3. So it will be this 3 into factorial 7 divided by 36 factorial 7. Now this factorial 7 will cancel. So we can write this as 1 minus 12 by 36, which is 2 by 3. So value of this probability is 2 by 3. Now we need to find the value of 12p. So 12p will be 12 into 2 by 3, which is nothing but 8, and that is the answer to this question. Now here the question is, there are 5 students S1, S2, S3, S4 and S5 in a music class. For them, there are 5 seats R1, R2, R3, R4 and R5 arranged in a row. When initially the seat Ri is allotted to the student Si, but on the examination day, the 5 students are randomly allotted the 5 seats. Now find the probability that on the examination day, student S1 gets the previously allotted seat R1 and none of the remaining student gets the seat previously allotted to him or her. Now if S1 goes to R1, there is only one way, and none of the remaining 4 students must get their previously allotted seat. That means we have to dearrange these 4 students, which is done by D4 divided by our total number of ways of arranging these 5 students in 5 places. It is factorial 5, and this is the required probability. Now we need to calculate D4. Now D4 is factorial 4, 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4. Now this is 12 minus 4 plus 1. So it will be 13 minus 4, 9. So this probability is 9 by 120, which is simply 3 by 40, and that's your option A. For I equals 1, 2, 3 and 4, let Ti denote the events that student Si and Si plus 1 do not sit adjacent to each other. Now T1 is S1 and S2, they are not adjacent. S2 and S3, they are not adjacent. S3 and S4, they are not adjacent, and S4 and S5, they are not adjacent to each other. So we need to find probability of S1 not sitting adjacent to S2, and S2 not sitting adjacent to S3, S3 not adjacent to S4, and S4 not adjacent to S5. Now here we have to consider certain cases. Now case 1 is when suppose S1 sits at R1. So S1 sits at R1. Now we have to choose possible combinations for remaining chairs R2, R3, R4 and R5. Now since S1, it cannot be adjacent to S2, so R2 can be filled by either S3, S4 or S5. Now S3, it cannot be adjacent to R2 and R4. So that means the only possible combination now here will be this S5. Now S5 cannot be next to S4. So this position, it has to be taken up by S2, and then finally it will be this S4. So we have this one combination which is S1, S3, S5, S2 and S4. Now if it is S4, it cannot have S3 and S5, so it will be this S2. Now then it will be this S5, and here we'll have S3. So we have this other case here. Now if it is S5, it cannot have S4. Now if it cannot have S4, then there are 2 possible options for R3, and they are either S2 or S3. Now if it is S2, it cannot have S3 as its partner, so then it will be this S4. Now the only option available is S3. Now in this case, it violates the condition, so it is not possible. Now if it is S3, it cannot have S2 and S4, and these are the ones which are remaining. So in this first case, we have only 2 choices. So for S1, we have only 2 choices. Now if we look at the second case when S2 takes R1. Now if S2 takes R1, then there are 2 possible options. Either it can be S4 or it can be S5. Now if it is S4 here, now 4 cannot have 3 or 5. So that means the next one has to be S1. And if it is S1, here it could be either S3 or S5. And if it is S3 here, we'll have S5, and here we'll have S3. So we have 2 cases here. And if it is
S5, it cannot have S4. So we can have either S1 or we can have S3. Now if it is S1, then we are left with S3 and S4. So if they are placed, they will be placed together. So we have no possibility here. And if it is S3, then next one will be S1 and then will be this S4. So we have three cases. So it will be these three cases now. Now if we look at S3, then the options here are either S1 or S5. Now if it is S1, then we can take S4, S5, and if it is S5, we can take S1, S2. Now if it is S4, then the next one, it has to be S2 followed by S5. So we have one case here. If it is S5, then it will be this S2 and S4. Again, this case is possible. Now if it is S1, then it will be S4, S2, and here it will be this S4 and S1. So for this third case, we have four possible arrangements. Now if we look at S1, S2, S3, S4 and S5. Now the condition for S1 is same as condition for S5, and condition for S2, it is same as condition for S4, and S3 has its condition of its own. So total number of favorable cases will be this 2 into 2 for S1 and S5 plus 2 into 3 for S2 and S4 plus 4, which is for S3, divided by total number of ways of arranging these 5 students in 5 places, which is simply factorial 5. Now this is 6 plus 4, 10, 10 plus 4, 14, 14 upon 120, which is 7 by 60. So this required probability is 7 by 60, and that's your option C. Now here the question is, let S be set of triplet A, B, C, where A, B and C are subsets of 1, 2, 3 up to n. Let even be the event that a selected triplet at random from set S will satisfy A intersection B intersection C equals 5, A intersection B unequal to 5, and B intersection C also unequal to 5. And A2 be the event that selected triplet at random from set S will satisfy the condition A intersection B intersection C is 5. Now A intersection B is unequal to 5, B intersection C is unequal to 5, and A intersection C is also unequal to 5. Now PE represents probability of an event. Find the probability of E1, and E1 is the intersection is 0, but A intersection B is non-zero and B intersection C is non-zero. Now if we look at total number of cases for this given set, we can choose any subset in 2 into 2 into 2 n times, that is 2 to the power n ways. So we have 2 to the power n choices for A, 2 to the power n choices for B, and 2 to the power n choices for C. So total number of choices will be 2 to the power n into 2 to the power n into 2 to the power n, which is simply 8 to the power n. Now we need to find this probability that A intersection B intersection C is 5, but A intersection B is unequal to 5 and B intersection C is also unequal to 5. Now if we look at the Venn diagram, now suppose this is A, B and C. So this is A, B and C. Now if we look at the regions, this is 1, 2, 3, 4, 5, 6, 7 and 8. Now we are given the condition that A intersection B intersection C is 5. So we are not supposed to choose this 7th number. So there should not be any element in this 7. And since A intersection B is unequal to 5 and B intersection C is unequal to 5, there should be at least one element in this region 2 and at least one element in this region 4. Another way to look at this 8 to the power n is, for every element there are 8 choices.
it can be placed in either of these 8 regions. So total number of choices we have for all the elements is 8 to the power n. Now for E1, we cannot put any element here. So for the remaining elements, we have 7 choices. So total number of choices will be 7 into 7 into 7, n times, and then minus all those cases in which at least 1 is missing from 2 or 4. So if 2 is missing, then in that case we have 6 to the power n choices. If 4 is missing, we have 6 to the power n choices. And here we have subtracted this case where both 2 and 4 are missing twice. So we need to add this case where both 2 and 4 they are missing. In that case, we need to add 5 to the power n to it, divided by total number of ways is 8 to the power n. So probability of E1 will be 7 to the power n minus 2 into 6 to the power n plus 5 to the power n divided by 8 to the power n, and that's your option B. Now it says find probability of E2. Now in E2, situation is same except for the condition that here this 6 must also not be empty. So in this also again we have total number of choices, which is 8 to the power n. Now 7 is empty, so total choices we have is 7 to the power n minus all those cases in which at least one of 2, 6 and 4 they are empty. So there will be 3C1, so there will be 3, and then one of them is missing, so it will be 6 to the power n, and then plus 2 of them they are missing, so there will be again 3C2, which is 3, 5 to the power n, and then minus all 3 of them they are missing. In that case, it will be simply 4 to the power n. So this problem is nothing but it's a simple inclusion exclusion problem. So answer to the second part is 7 to the power n minus 3 into 6 to the power n plus 3 into 5 to the power n minus 4 to the power n upon 8 to the power n, which again is option B. Now here the question is, two numbers x and y are chosen at random from the set 1, 2, 3 up to 3n. Find the probability that x square minus y square is divisible by 3. Now what we'll do is we'll partition this set in 3 parts according to the remainder when the numbers are divided by 3. So we'll have this first set, say S1, in which we have numbers which are multiples of 3 and which will leave the remainder 0 when divided by 3, and number of numbers in this set is n. Now we have the second set which leaves the remainder 1. It'll have 4, 7, 10, and again it'll have n such numbers, and this third set which is 5, 8, 11, leaving the remainder 2 when divided by 3, and again we have n such numbers. So what we have done is we have partitioned this set in 3 sets. Now we need to find the probability that x square minus y square is divisible by 3. Now we can write x square minus y square as x minus y into x plus y. Now this number will be divisible by 3 when x minus y is divisible by 3. Now, it will be divisible by 3 if both the numbers they are either from S1 or both of them they are from S2 or both of them they are from S3. So this required probability will be simply, now NE2 from this set will be given by NC2. Now for S2 also it will be NC2, and for S3 also it will be NC2. So there will be 3 into NC2 plus, now this x plus y will be divisible by 3 if either both the numbers they are from this set S1, which we have already included, or when one number is from S2 and the other number is from S3. And in this case we have NC1 and NC1. In that case, sum of remainders will be 3. So this number x plus y will be divisible by 3. So this required probability will be favorable divided by total. Now total number of ways of choosing 2 from these 3n numbers will be simply 3n C2. Now this is 3n n minus 1 by 2 plus n square, and here will be 3n minus 1 whole divided by 2. Now this is 3n square plus 2n square, and there will be 5n square minus 3n upon 3n into 3n minus 1. So this required probability will be 5n minus 3 upon 3 into 3n minus 1, and that is the answer to this question. So that's your first part. Now here the question is, there are m red socks and n blue socks where m is greater than n in a cupboard, and they are well mixed up, where m plus n is less than or equal to 101. If two socks are taken out at random, the chance that they have the same color, it is 1 by 2. Find the largest possible value of m. Now we need to find the probability that they are of the same color. So if they are both red, then this is MC2. If they are both blue, it will be simply NC2 divided by m plus n C2. Now this probability is 1 by 2. Now we solve this, we'll get m minus 1 plus n minus 1 divided by 2. So this 2 will cancel, and here will be this m plus n, and it will be m plus n minus 1, and it should be this 1 by 2. Now we simplify this, we'll get this as 2m square plus 2n square minus 2m minus 2n, and here will be m plus n whole square, which is m square plus n square plus 2mn minus m minus n. Now m square n square will cancel once, and then m and n will also cancel, so it will cancel. From here we'll get this condition that m square plus n square minus 2mn will be equal to m plus n, or m minus n whole square will be equal to m plus n. Now this m plus n, it is less than or equal to 101. We can write m minus n, it is less than or equal to under root of 101. Now we have two conditions. M minus n, it is less than or equal to under root 101, and m plus n, it is less than or equal to 101. So if we add them, we get 2m, it should be less than or equal to 101 plus, and this is 10 point something. So it will be 111 divided by 2. So this m, it should be less than or equal to 111 point something divided by 2, which is 55 point something. So the maximum possible or the largest possible value of m is simply 55, and that is the answer to this question. Now here the question is, in a box there are 8 alphabets cards with letters SS, AAA, HH and H. Find the probability that the word H will be formed if, now the first part is, the 3 cards are drawn one by one and placed on the table in the same order as they are drawn. Now in order to form this word H, this first card, it must be A, and the probability that first card will be A will be given by 3 divided by 8. So there will be 3 by 8. Now for next letter to be S, it should be 2 by 7, and finally it should be H, which again is 3 by 6. Now it'll cancel, so this probability will be 3 by 56. So if the cards are drawn one by one and placed in the same order, then this required probability will be 3 by 56. Now if we come to the second case, when 3 cards are drawn simultaneously, now in this case we need to choose any one out of these 2s, so it will be 2c1, any one out of 3a's, so it will be 3c1, and any one out of 3h, so there will be 3c1 divided by 8c3. Now this is 2 into 3 into 3, and there will be 8, 7, 6, and this is 3, 2 and 1. So in this case, this 6 will cancel. Now it will be 4, so there will be 9 by 28. So if the cards are drawn one by one, then this probability is 3 by 56. But if they are drawn simultaneously, then this probability will be 9 by 28. Now here the question is, a bag contains 12 red balls and 6 white balls. Now 6 balls are drawn one after other without replacement, of which at least 4 balls are white. Now find the probability that in the next 2 draws exactly 1 white ball is drawn. Leave the answer in terms of NCR. Now it says there are at least 4 balls which are white. So we'll have two cases. Case 1 when we have 4 white and 2 red, or this case when we have 5 white and 1 red. If we find this probability, 4 white is 6C4 into 12C2 divided by 18C6, and here will be 6C5 into 12C1 upon 18C6. And in this case, we are left with 2 white and 10 red balls, and in this case we are left with 1 white and 11 red balls. Now it says in the next 2 draws exactly 1 white ball is drawn. So for the next stage we have to select any 2 from these 12. So it will be this 12C2, and this one should be white and the other one should be red. So it will be this 2C1 into 10C1. In the same way for this one also it will be this 12C2, and this is 1C1 into 11C1. So this required probability is sum of these two, which is the answer to this question. Now here the question is 8 players P1, P2, P3 and P8, they play a knockout tournament. It is known that whenever the players Pi and Pj play, then the player Pi will win if I is less than j. Now assuming that players are paired at random in each round, what is the probability that player P4 reaches the final? Now if we look at this first stage, then from these 8 we have to make pairs of 2, 2, 2 and 2, and it can be done in factorial 8 divided by factorial 2 to the power 4 divided by factorial 4. Now this is 8, 7, 6 and 5, and this is 16. So it will be 21 into 5, and there will be 105. So in the first stage we have 105 possible combinations. Now this P4, he has to reach final, and the final we know that P1 is going to be there and we should have P4. Now P1, it can be paired against anyone, but for P4 to be in the final, P4 has to be paired with someone which is greater than 4. So that means in the first stage when we have P1, P2, P3, P4, P5, P6, P7 and P8. So in the first stage, if P4 has to reach the next stage, this P4, it must be paired with any one of these P5, P6, P7 and P8, and also we should have another pair from the same set where we have PA and PB. So in the first stage, we have 4 possible combinations for P4. So suppose we have selected any one, say P6. Now out of these 3, we have to choose another pair. So that means from the remaining 3, we have to choose any 2, and it can be done in 3C 2 ways. So suppose we have selected P5 and P7. Now we are left with these 4 people, P1, P2, P3 and P8. Now for this P8, we can choose any one partner from P1, P2 and P3, and it can be done in 3C 1 ways, and remaining 2, they'll form the last pair. So in the second round, now we'll have 4 players. P1 will be there, P4 will be there, and then out of P2 and P3, one of them will be there. We'll say, suppose this is PH, P high, and then one from lower, and there'll be PL. So the probability that P4 goes to this next stage will be this value divided by total combinations, and which is 105. Now P4 has to reach final. P4 will reach final if and only if this P4, it is paired with PL, which is lower value of P5, P6, P7, P8, which was there from the first round. So in this case, this P4, it has to be paired with PL, and this can be done in 1 by 3 ways. So this required probability will be 4 into 3 into 3, 36 divided by 105 into 3. Now this is 12 and this is 4 by 35. So the probability that P4 reaches final, it is 4 by 35, and that is the answer to this question. Now here the question is, an unbiased die with faces numbered 1, 2, 3, 4, 5, 6 is thrown n times and the list of n numbers showing up is noted. What is the probability that among the numbers 1, 2, 3, 4, 5, 6, only 3 numbers appear in the list? So it says from these 6 numbers, only 3 of them they appear when we throw this die n times. Now first we'll choose which 3. So from these 6, we can choose any 3 numbers in 6C 3 ways. Now once we have 3 numbers, say 1, 2 and 3, then total number of possible combinations that we can have is 3 into 3 into 3 n times, and there will be 3 to the power n. Now from this we have to remove all those cases in which at least 1 is missing. So from this we'll remove minus this case when 1 is missing. So there will be 2 to the power n. If 2 is missing, that also is 2 to the power n, and if 3 is missing, that also is 2 to the power n. So from 3 to the power n, we'll subtract 3 into 2 to the power n. So this is na plus nb plus nc. Now from this, we'll add all those cases in which 2 of them they are missing. So if 2 or 3 they are missing, we'll have only one case. So we have to add these numbers 3 times. Now we need to find this required probability. So this required probability will be this favorable case upon, now total number of ways is simply 6 to the power n. So this required probability will be 20 into 3 to the power n minus 3 into 2 to the power n plus 3 upon 6 to the power n, and that is the answer to this question. Now here the question is, suppose there are 5 red points and 4 blue points on a circle. So we have this circle on which we have 5 red points, 1, 2, 3, 4 and 5, and then we have 4 blue points, 1, 2, 3 and 4. Let m by n be the probability that a convex polygon whose vertices are among the 9 points has at least one blue vertex where m and n are relatively prime. Find the value of m plus n. Now we need to find the probability that a convex polygon whose vertices are among 9 points has at least one blue vertex. Now first we'll find number of ways in which we can form this polygon. Now this polygon, it can be a triangle, so which is given by 9C3. It can be a quadrilateral 9C4. We'll continue and we'll go all the way up to 9C9. It will be 2 to the power 9 minus 9C0 minus 9C1 minus 9C2, which is 2 to the power 9 is 512 minus 1 minus 9, and this is 36. It will be 466. So from these 9 points, 466 convex polygons can be formed. Now from this we'll subtract all those cases in which a polygon doesn't have a blue vertex. So number of favorable cases will be this total 466 minus all those cases when we do not have a blue vertex. So triangles that can be formed from these 5 red will be 5C3 minus quadrilaterals and minus pentagon, which is 5C5. So this is 466 minus, now this is 10 minus 5 minus 1, so it will be 16. So this value, it is nothing but 450. So this required probability that it will have at least one blue vertex will be given by 450 upon 466, and there will be 225 upon 233, and this is equal to m by n. Now we need to find the value of m plus n, so it will be simply 225 plus 233, and there will be 458, and that is the answer to this question. Now here the question is, 2n boys are randomly divided into 2 subgroups containing n boys each. The probability that the 2 tallest boys are in different groups is. Now first we'll define total number of ways of distributing 2n students in group of n and n. Now this can be done in factorial 2n upon factorial n whole square divided by factorial 2. Now, if we keep two tallest boys aside, say T1 and T2, then we are left with 2n minus 2 people, which we have to divide in groups of n minus 1 and n minus 1, which can be done in factorial 2n minus 2 upon factorial n minus 1 whole square factorial 2. Now, once we have these two groups, in these two groups, we can distribute these two boys in factorial 2 ways. So this required probability will be factorial 2n minus 2 into factorial 2 upon factorial n minus 1 square into factorial 2, and this is factorial 2n factorial n square, and this is factorial 2. Now I'll cancel. Here will be this n square into 2, and here it will be this 2n into 2n minus 1. Now this 2n will cancel. So this required probability will be n upon 2n minus 1, and that's your option A. Now here the question is, a bag contains 7 tickets marked with numbers 0, 1, 2, 3, 4, 5 and 6. A ticket is drawn and replaced. Then the chance that after 4 drawings, the sum of numbers drawn is 8. Now here we have 4 drawings. Now let the number on the first drawing be x1, and the second be x2, third one be x3, and fourth one be x4, and it should be equal to 8, where each of xi can take the value from 0 to 6. Now we can model the problem using binomial theorem. So we need to find coefficient of x to the power 8 in the expansion of 1 plus x square up to x to the power 6 whole to the power 4. So we need to find coefficient of x to the power 8 in, so now this is 1 minus x to the power 7 upon 1 minus x to the power 4. Now we can add this as 1 minus, this is 4c1, 4 into x to the power 7. We'll disregard higher powers into 1 minus x to the power minus 4. Now we'll get x to the power 8 when x to the power 8 gets multiplied with 1, and when x to the power 1 gets multiplied with 4 into x to the power 7. So this coefficient of x to the power 8 will be 1 into coefficient of x to the power 8 in 1 minus x to the power minus 4, and then minus 4 into coefficient of x in 1 minus x to the power minus 4. Now we know that coefficient of x to the power r in the expansion of 1 minus x to the power minus n will be n plus r minus 1 cr. So we can write this as 1 into, and this is 4 plus 8 minus 1 c8, and then minus 4, and this is 4 plus 1 minus 1 c1. Now this is 11 c8 minus 16, and this value is 11, 10, 9, and then 3, 2, minus 16. Now this is 3 and 5, 165 minus 16, and there will be 149. So this is our favorable number of cases. Now total number of cases will be, for each drawing we have 7 choices. So total number of choices will be 7 into 7 into 7, 7 to the power 4. So this required probability is going to be 149 divided by 7 to the power 4, which is 2401, and that's your option B. Now here the question is, let the sides of a triangle be decided by throwing a die thrice. If the probability that triangle is isosceles or equilateral is P by Q, where P and Q are relatively prime positive integers, then Q minus P is. Now when we throw a dice thrice, then we'll get some numbers. In some cases a triangle may be possible, and in other cases a triangle is not possible. Now what we'll do is we'll start counting number of equilateral triangles. Now if we look at number of equilateral triangles, there will be 6 cases when we have 1, 1, 1, 2, 2, 2 up to 6, 6 and 6, So there will be overall 6 equilateral triangles. Now next we'll consider triangles which are isosceles but not equilateral triangles. Now with 1 we can only have 1, 1, 1. 1, 1, 2 will be a straight line. So the first isosceles triangle we'll get is with 2. So it will be this 2, 2, 1, then 2, 2, 2 will be an equilateral triangle. Then we'll have 2, 2, 3. Now 2, 2, 4 will be a straight line. And the same way we'll have 3, 3, 1, 3, 3, 2. Now 3, 3, 3 is equilateral. We'll have 3, 3, 4 and 3, 3, 5. 3, 3, 6 is again a straight line. Then we'll have 4, 4, 1, 4, 4, 2, 4, 4, 3. We'll discard 4, 4, 4. Then 4, 4, 5 and 4, 4 and 6. So we have 2 cases here, 4 cases here and 5 cases here. For 5 also we'll have 5 cases except for 5, 5 and 5. And for 6 also we'll have 5 cases here. So total number of isosceles triangles which are possible is 15 plus 6 and there will be 21. Now if we look at scalene triangles, now for scalene triangle, if we consider smallest side as 1, then we'll get either an equilateral triangle or an isosceles triangle. There is no other way possible. Now we'll consider 2. Now if it is 2, then one of the triangle possible is 2, 3, 4. Now 2, 3, 5 is a straight line. And then we'll have 2, 4, 5. And also 2, 5, 6. And the same way smallest side is 3. Then we'll have 3, 4, 5. We'll also have 3, 4, 6. And then we'll have 3, 5, 6. And also it will be this 4, 5, 6 considering smallest side is 4. So here we have 7 cases. So there will be these 7 scalene triangles. Now total number of triangles that are possible will be this 6 plus 21 plus 7, which is 28 plus 6, 34. And out of these 34 triangles, the triangles which are either isosceles or equilateral, there are 6 plus 21, which is 27. So this required probability that triangle is either isosceles or equilateral will be this 27 by 34, which is given as P by Q. Now we need to find the value of Q minus P. Now 34 minus 7, it is 7. So answer to this question is 7. Now the question is, let V and W be distinct randomly chosen roots of the equation z to the power 1997 minus 1 equals 0, and let m by n be the probability that root of 2 plus root 3 is less than or equal to mod of v plus w, where m and n are relatively prime positive integers. Find m plus n. Now basically these are nth root of unity. Now one of the root is 1, and then we have alpha square. If we find angle between any two successive roots, and suppose that is theta, this angle is given by 360 divided by 1997. So that is the smallest possible unit of angle. Now we need to choose two roots v and w such that mod of v plus w is greater than or equal to root of 2 plus root 3. Now suppose we have two roots, say v and w, and angle between them is say alpha, then we can write mod of v plus w is greater than or equal to 2 plus root 3. Now we know that
Modulus of cube root of unity is 1. So this is 1 plus 1 plus 2 cos alpha and will be greater than or equal to 2 plus root 3. Now 2 and 2 will cancel. So from here we'll get this condition that cos alpha is greater than or equal to root 3 by 2, or from here we can say value of alpha should lie between 0 and 30 degrees. Now suppose we choose any one root, then for this condition to be true, we have to choose the other root so that this angle is less than or equal to 30. Now we need to find how many choices do we have for such cases. So it will be this 0 and then n times theta should always be less than or equal to 30. Now this is 0 and this is n, theta is 360 upon 1997 is less than or equal to 30. Now we simplify this, we'll get the value of n between 0 and 166.41. Now we cannot take 0 because then it will be the same root and n has to be integer. So we can choose this other root in 166 ways for this to be true. Now this angle, it can be either clockwise or it can be in the anti-clockwise direction. So we have 166 other roots in other direction. So total number of favorable ways in which mod of u plus w will be greater than or equal to root of 2 plus root 3 is given by 332. So for any root, we have 332 favorable positions. So this required probability will be this 332 divided by, now how many total choices do we have? So there are 1997 roots, out of which 1 is V. So the remaining ones are 1996. So the required probability is 332 upon 1996, which is simply 83 by 499. And that is the answer to this question. Now the question is, consider the sets A and B. The probability of getting an increasing function from A to B when a mapping is selected at random from the set of all mappings from A to B. Now total number of mappings in this case will be, now for each of these three elements we have 6 choices. So it will be this 6 into 6 into 6 and there will be 206 possible mappings. Now the first one is find the probability that we get an increasing function. Now in order to get an increasing function, we need to select 3 out of these 6. So it can be done in 6 C3 ways. And since they are to be arranged in increasing order, there is only one arrangement. So it will be this 6C3 upon 216. Now this is 5 into 4 upon 216, which is 5 by 54. And that's your option C. Now the second one is probability of getting a non-decreasing function from A to B when a mapping is selected at random from the set of all mappings. Now non-decreasing mapping or non-increasing mapping, we have already studied it on one of the previous videos. So there the fundamental is, if we have two sets A and B, A containing n elements and B containing m elements, then number of non-increasing or non-decreasing functions, it is given by n plus m minus 1 Cn. So in this case, this probability will be simply 3 plus 6 minus 1 C3 divided by 216. Now this is 8C3, which is 8 into 7 divided by 216. Now this is 7 by 27, and that's your option A. And then we have this third one, which is the probability of getting an onto function from B to B such that Fi is unequal to I when a mapping is selected at random from the set of all mappings from B to B. Now here in this third question, we are considering mappings from B to B. Now total number of mappings from B to B will be this 6 to the power 6. Now are these mappings? We have to find all the mappings in which the function is an onto function and Fi is unequal to I. So basically this is nothing but derangement of 6 objects. So it will be nothing but D6. Now D6 is 265. So it will be this 265 upon 6 to the power 6. which actually doesn't match with any of the option. But if we take this question as getting a function such that fi is unequal to I, given that it is an onto function, then this probability, it comes out as d6, and number of onto functions from b to b will be simply factorial 6. So if we take d6, which is 265 upon factorial 6, we'll get this result as 53 upon 144, and that's your option C. But the way the question is given, it should be this 265 upon 6 to the power 6. Now the question is, consider a function f defined from the set 1, 2, 3 up to 13 to 1, 2, 3 up to 9, given that this function is surjective and non-decreasing, then probability that f7 equals 4 is. Now we have this set containing 13 elements. 1, 2, 3, 6, 7, 8 up to 13, and here we have 9 elements from 1, 2, 3, 4 up to 9. Now first we will find total number of ways in which this given function can be surjective and non-decreasing. Now it will be surjective and non-decreasing if this one, it is mapped to this one, and it may also map to 2 or 3 whatever, and this 13, it has to be mapped to 9. Now what we'll do is we'll say these first two, say x1, they'll be mapped to 1, then x2, they'll be mapped to 2, and then we'll have x9, which are mapped to 9. So x1 plus x2 plus x9, it must be equal to 13, where each of xi, it must be greater than or equal to 1. At least one of the elements should be mapped to each element in B, so that this function can be a surjective function. So in this case, we just need to find number of positive integral solutions. Now number of positive integral solutions is given by n minus 1 c r minus 1, which is nothing but 12c8. So total number of ways in which these functions can be defined so that function is both surjective and non-decreasing, it is 12c8. Now in the favorable case, we have this 7, which is mapped to 4. Now if 7 is mapped to 4, then in how many ways we can define this function? So for these first 4 elements, we can write x1 plus x2 plus x3 plus x4, and it should be equal to 7, where each xi is, it is greater than or equal to 1. Now number of positive integral solutions in this case will be 7 minus 1, c 4 minus 1, and that will be 6 c3, and again from 4 to 9 we can write x4 plus x5 plus x6 plus x7, x8 plus x9, and that will be equal to 7, and here we will take this as x4 dash, because we are talking about all the image of 4 from 7 to 13. Now again, number of positive integral solutions will be 7 minus 1, c 6 minus 1, which is 6c5 or 6c1. So this required probability will be 6c3 into 6c1 upon 12c8, and that's your option D. Now the question is, if n different objects are distributed among n plus 2 persons, then the probability that exactly 2 persons will get nothing is. Now total number of ways of distributing these n objects among n plus 2 people will be, now for each object we have n plus 2 options. So total number of ways of distributing these n objects will be n plus 2, n plus 2, n plus 2, n times, and there will be n plus 2 to the power n. Now in this first case, when we have distributed them so that exactly 2 people get nothing, in this case we have to select, are these n plus 2 which 2, and it can be done in
n plus 2, C 2 ways. Now we are left with n objects and n people. And here, since we have n people and n objects, so each person should get exactly one object. Now n different in n places can be distributed in factorial n ways. So this required probability that exactly 2 are left, it is given by n plus 2 C2 into factorial n divided by n plus 2 to the power n. Now this is n plus 2, n plus 1, factorial n, and this is 2 and n plus 2 to the power n. Now this is factorial n plus 1 upon 2, and this is n plus 2 to the power n minus 1. That means this option A, it is correct, and option D, it will be incorrect. Now in the second part it says probably that exactly 3 persons will get nothing. Now which 3? So first we'll select these 3 people from n plus 2, and which can be done in n plus 2 C3 ways. Now we have n objects and n minus 1 people. Now out of these n minus 1 people, one of them will get 2 objects and remaining people will get exactly 1 each. Now which person gets these 2 objects? So we can select it in n minus 1 C1 ways, and which 2 objects? So from the n we can select it NC2 ways. Now we are left with n minus 2 people and n minus 2 objects, which can be arranged in factorial n minus 2 ways. Now this required probability will be total number of cases, which is n plus 2 to the power n. So this probability is n plus 2 C3 into n minus 1 NC2 n minus 2 factorial upon n plus 2 to the power n. That means this option B is correct and option C is incorrect. So the correct options are A and B.